What if black holes have no center? Imagine staring into the heart of a black hole, a place so mysterious, so powerful that not even light can escape. For decades, scientists believed that deep inside these cosmic monsters lies a singularity, a single point where gravity crushes everything to infinite density and time itself comes to a stop. But what if that's not the case? What if black holes don't have a center at all? Could the center of a black hole be something else entirely, like a bouncing gateway to another universe, or a swirling loop in the fabric of space-time? Let's dive into this cosmic mystery and explore what it really means if black holes have no center. A singularity is a mysterious idea in science. It describes a place or condition where gravity becomes so incredibly strong that it completely breaks down the usual rules of space and time. In this extreme situation, space and time don't work the way we normally understand them. They stop making sense altogether. Because of this, a singularity isn't something we can talk about in terms of where it is or when it happens. It exists outside the normal fabric of the universe. Singularities sit at the strange crossroads between two major theories in physics: general relativity, which deals with gravity and large-scale structures like stars and galaxies, and quantum mechanics, which explains the behavior of tiny particles like atoms. The problem is, we still don't have a single theory that perfectly combines both of these ideas. This missing piece is sometimes called quantum gravity. Without it, we can't fully understand or describe what's really going on inside a singularity. Scientists have been trying for a long time to clearly define what a singularity is in terms of general relativity, which is currently our best theory about gravity. Some say it happens when the curvature of space becomes infinite, basically when space bends so sharply that it breaks. Others say it's better defined by geodesics, the paths that objects naturally follow in space, suddenly ending or becoming incomplete, as if the universe itself has reached a dead end. According to general relativity, if a massive object like a star collapses past a certain point, this is known as the Schwarzchild radius, it will turn into a black hole. At the very center of that black hole, hidden behind what's called an event horizon, a point of no return, a singularity is formed. At that point, the density of matter becomes infinite. The theory also says that the universe itself began as a singularity, an unimaginably hot and dense point, at the very beginning of time, during the Big Bang. But there's a problem. General relativity isn't expected to work in those extreme situations. At those points, we need quantum mechanics to take over. And quantum physics tells us that particles can't be squeezed into a space smaller than a certain size, known as their Compton wavelength. This means that the idea of infinite density doesn't quite work under quantum rules. In fact, many areas of physics involve what are called mathematical singularities. These are points in equations where things go wild, numbers become infinitely large, or stop making sense. This usually means that the theory we're using is incomplete. Examples include the old problem known as the ultraviolet catastrophe, the need for a process called renormalization, and the instability predicted for hydrogen atoms in older models using the Llama formula. In older theories like classical field theory, including special relativity but not general relativity, a singularity is just a place in space and time where the math breaks down. In those cases, space and time themselves are still working normally, and the singularity is just a weird spot in that system. But in general relativity, things are far more dramatic. The singularity actually breaks space and time, making them undefined. That's why we can't describe a singularity using regular ideas of here and now. Interestingly, some newer theories suggest that singularities might not even be real. For example, loop quantum gravity, a theory that tries to blend quantum mechanics and gravity, proposes that space is made up of tiny loops and that there's a smallest possible size for space. In this view, gravity stops getting stronger once things are compressed to that smallest size. Instead of becoming infinite, gravity reaches a limit. Some theories even suggest that the waves of particles themselves spread out in such a way that they hide or cancel out the effects of intense gravity at very small scales. Inspired by ideas from loop quantum gravity, some scientists have explored whether singularities can be avoided by rethinking the very basics of geometry. They've looked at the first axiom of geometry, which is the idea of a point. Instead of thinking of a point as something with no size, they consider it as a tiny but extended area. This idea comes from the work of mathematician Felix Klein, who believed that geometry and arithmetic could be fused together. According to physicist Max Born, Klein's approach was a way of recognizing the natural uncertainty that exists in all observations of the physical world. It's also important to understand that not all singularities are the same. They can take different shapes and appear in different ways depending on the theory. Some might be conical, like the tip of an ice cream cone, while others might be more curved. Some scientists have even suggested that singularities could exist without being hidden behind an event horizon. These are called naked singularities, and they would be visible to the rest of the universe, which would completely change our understanding of how the cosmos works. A conical singularity is a strange and fascinating point in space where the normal, smooth structure of the universe breaks down. Imagine a perfectly smooth sheet of paper that suddenly forms a sharp point, like the tip of a cone. At this tip, the usual mathematical tools that describe space and time stop working properly. This is because, at this point, certain important quantities, ones that are supposed to stay the same no matter how you measure them, either do not settle down to a clear value or become infinitely large. That's why scientists say space-time is not smooth at that exact spot. Interestingly, this breakdown doesn't necessarily mean chaos everywhere. Outside that sharp tip, the rest of space can still behave normally and have well-defined measurements. A real-world example of this kind of singularity can be found in theoretical objects like cosmic strings, thin, incredibly dense lines of energy stretching across the universe. And in the case of a Schwarzchild black hole, which is a simple kind of black hole that doesn't spin and carries no electric charge. When physicists try to solve the complicated equations of Einstein's general theory of relativity, or even more complex theories like supergravity, they often run into places where the values in their equations explode to infinity. But here's the twist. Not all of these infinities mean there's something truly wrong or broken. Sometimes they only pop up because the scientist has chosen a poor way to describe the point, like looking at a map that distorts the real shape of a country. To really figure out if a singularity is there, scientists must look at special quantities called scalars, which do not change no matter how the coordinates are set up. If these scalars become infinite, then the singularity is real and cannot be explained away by simply changing the coordinate system. One famous example is the Schwarzchild solution, which describes a simple black hole. When using certain coordinates that work well far from the black hole, the math becomes infinite right at the event horizon, the invisible boundary where nothing, not even light, can escape. But this infinity is just a trick of the coordinates. If you switch to a different set of coordinates, called Kruskal coordinates, everything looks smooth again at the event horizon. However, things are different at the very center of the black hole. There, even the best coordinate systems can't hide the fact that the math blows up. One way scientists know the singularity is real is by calculating something called the Kretschmann scala, which involves squaring parts of a complicated mathematical object called the Riemann tensor. This scala becomes truly infinite at the center, confirming the presence of a singularity. In the case of a non-spinning Schwarzschild black hole, the singularity is a single point, a point singularity. But for a spinning black hole, called a Kerr black hole, the singularity stretches into a loop, forming a ring singularity. Theoretical physicists have even proposed that this ring-shaped singularity could be the entrance to a wormhole, a tunnel that might connect distant parts of space and time. More broadly, scientists say that space-time contains a singularity if it is geodesically incomplete. That's a fancy way of saying there are paths that a falling object could take that suddenly stop, as if space itself runs out. For example, if someone fell into a non-rotating black hole, they would reach the singularity at the center in a finite amount of time. They couldn't continue their journey beyond that point, no matter what. The classical Big Bang model also includes a singularity at the very beginning of the universe, at time zero. At this hypothetical moment, the entire universe was squeezed into a point of infinite density, infinite temperature, and infinite curvature. There was no before this point in time, because all the usual rules of physics break down there. For many years, up until the early 1990s, scientists believed that all singularities were hidden safely inside black holes, behind event horizons. This idea is known as the cosmic censorship hypothesis. But in 1991, physicists Stuart Shapiro and Sol Tucholsky ran computer simulations of a rotating flat disk made of dust. Their results suggested that a singularity might form without an event horizon around it. This kind of singularity, called a naked singularity, would be visible to the outside universe. What such an object might actually look like is still a mystery. It's also unclear whether these strange results would still happen if the simulation were made more realistic. However, some scientists think that even in this case, light entering the singularity would behave in a way that makes the object look like a black hole anyway, since light paths, or geodesics, would also come to an abrupt end. Interestingly, event horizons can disappear in the Kerr solution, the spinning black hole model, if the black hole is spinning fast enough. In that case, the singularity might be exposed to the outside world, creating a real possibility for a naked singularity. Before Stephen Hawking introduced the idea of Hawking radiation, most physicists avoided the question of whether black holes could have entropy, a measure of disorder and heat. But Hawking showed that black holes do give off energy like a glowing object through a slow and mysterious process. This discovery helped solve a big problem. It showed that black holes do not violate the second law of thermodynamics, which says that total entropy in the universe should never decrease. Since entropy is linked to temperature, this meant that black holes must have a temperature too. Because black holes lose energy by emitting radiation, they will not last forever. Over time, they will slowly evaporate and shrink. Interestingly, the temperature of a black hole is inversely related to its mass. So, the bigger the black hole, the colder it is. All the black holes scientists have found so far are so massive that their temperatures are much colder than the background temperature of the universe. This means they are actually gaining energy, not losing it. Black holes won't start shrinking until the cosmic background radiation cools down enough to fall below the black hole's own temperature. This will only happen when the redshift of the universe increases to more than 1 million, a huge change compared to the current redshift of only about 1,000, which happened when the background radiation first formed. The holographic principle is an amazing idea that comes from string theory and the field of quantum gravity. It suggests something quite surprising, that everything happening inside a space, like the entire contents of a room or even the whole universe, could actually be described using information stored on a surface that surrounds it. This surface would have fewer dimensions than the space itself. You can think of it like a hologram, where a flat image can appear three-dimensional when viewed from certain angles. In the same way, the universe might be a three-dimensional projection of something written on a faraway two-dimensional surface, like the edge of space itself, or the boundary around a black hole. This fascinating idea was first introduced by Gerard 't Hooft and then expanded and made clearer by Leonard Susskind, a physicist who used ideas from string theory to explain it more precisely. Susskind was inspired by both 't Hooft and another physicist named Charles Thorne, who had also been thinking along similar lines. Susskind once explained it like this: the three-dimensional world we live in, with stars, planets, houses, mountains, and people, the three-dimensional world we live in, with stars, planets, houses, mountains, and people, is actually like a hologram. It's an image of reality written on a faraway, two-dimensional surface. In the year 1978, Charles Thorne noticed something remarkable in string theory. He found that it allows for a description of gravity using fewer dimensions. Later, Raphael Bousso pointed out that Thorne's observation was actually an early version of what we now call holography. One of the best-known examples of this idea is something called the ADS-CFT correspondence, a powerful concept that connects two very different theories in physics and shows how the holographic principle might work in practice. The holographic principle was deeply inspired by a concept from black hole physics called the Beakenstein bound. This idea says that the amount of disorder, or entropy, in any region of space doesn't increase with the volume, which grows as the cube of the radius, but with the area of the boundary, which grows with the radius squared. This was a surprising insight because it means that the surface of something, not its inside, might hold all the information about it. In the case of a black hole, this means that everything that falls in might be encoded on the black hole's event horizon, the surface that marks the point of no return. The holographic principle even helps solve a long-standing puzzle called the black hole information paradox. This paradox asks, if something falls into a black hole, is its information lost forever? The holographic principle says no, the information isn't lost, it's stored on the surface. But things aren't that simple. Some scientists have found strange solutions to Einstein's equations that seem to allow more entropy than the holographic principle would allow. These unusual situations are called Wheeler's bags of gold. They seem to show that more information can be stored in a region than just on its surface. These examples don't fit well with the holographic idea, and physicists are still trying to figure out how to deal with them in a theory that includes quantum gravity. Now, let's step back and look at an even bigger picture. Most people think the universe is made of matter and energy, the things we can see, touch, or measure. But in an article published in 2003 in Scientific American, physicist Jacob Beakenstein explored a bold new way of thinking. He talked about a trend started by John Archibald Wheeler, who suggested that maybe the universe is really made of information, and that matter and energy are just side effects. Beakenstein even asked, quoting poet William Blake, "Could we see a world in a grain of sand?" hinting at the idea that all of reality might be contained in something incredibly small and simple, just like a hologram. In his article called A Tale of Two Entropies, Beakenstein explored how Wheeler's idea might have deep meaning. He pointed out a surprising connection between information theory, which deals with how data is stored and communicated, and classical physics, the science of motion and forces. This connection was first noticed shortly after the famous papers written in 1948 by Claude Shannon, an American mathematician. Shannon introduced the idea of Shannon entropy, a way to measure how much information is in a message or a system. Shannon entropy became one of the most important ideas in the world of technology. It's used in everything from cell phones and modems to hard drives and DVDs. Without Shannon's discovery, our modern world of communication and data storage wouldn't exist. So, the holographic principle isn't just about black holes or distant galaxies. It's part of a much bigger story, one that connects the deepest laws of physics with the way we understand information, and maybe even with how we understand reality itself. In the world of physics, there's a special area called thermodynamics, which focuses on understanding heat and how it moves. One of the most important ideas in thermodynamics is something called entropy. A common way to describe entropy is to say it's a measure of how disordered or messy a system is. That is, how mixed up the particles of matter and energy are. But in the year 1877, An Austrian scientist named Ludwig Boltzmann gave a more precise explanation. He said that entropy tells us how many different microscopic ways, or arrangements, tiny particles like atoms and molecules can be set up, while still making the whole system look the same from the outside. For example, if we think about the air in a room, there are countless ways the molecules of gas can be spread out and move around. Even though all these microscopic arrangements might look identical on a large scale, Boltzmann's idea was that each of those invisible arrangements adds to the total entropy. Boltzmann even found a mathematical formula to describe this. It uses something called a logarithm, which helps deal with really huge numbers, because there are so many possible ways the air molecules can move and be positioned. Many years later, a man named Claude Shannon, who was working in a totally different field, information theory, made a surprising discovery. While trying to figure out how to measure the amount of information in things like telegraph messages, he came up with a formula that looked just like Boltzmann's. Shannon's work helped lay the foundations for modern computing and digital communication. In August of 2003, a scientist named Jacob Bekenstein wrote an article for Scientific American called Information in the Holographic Universe. In it, he pointed out something fascinating. Even though Boltzmann was working with heat and matter, and Shannon was working with messages and data, both were really measuring the same thing: the number of different ways a system can be arranged. The only difference was the units they used. Thermodynamic entropy is measured in terms of energy and temperature, while Shannon's information entropy is measured in bits, which are like the basic building blocks of digital information. Now, here's where things get even stranger and more fascinating. There's a bold idea in physics called the holographic principle. It says that everything in the universe, all matter, energy, and space, might actually be like a hologram. That means everything we experience in 3 dimensions might really just be a projection from a 2-dimensional surface, like the outer edge of the universe. According to this principle, entropy doesn't depend on the volume of space, like you might expect. Instead, it depends on the surface area of the region, as if all the information about what's inside is written on the outside. This idea is deeply connected to something called the AD-S-CFT correspondence, also known as the Maldacena duality, named after physicist Juan Maldacena, who first proposed it in late 1997. This is a mind-bending concept that connects 2 very different kinds of theories. On one side, there are models of curved space known as anti-de Sitter spaces, or ADS, used in string theory and quantum gravity. On the other side, there are conformal field theories, or CFTs, which are powerful mathematical tools used to describe particles and forces, like those in quantum physics. What makes this duality so amazing is that it gives scientists a new way to explore extremely complicated quantum systems. When things are very hard to understand on the quantum side, the duality often lets physicists switch over to the gravity side, where the math becomes easier to handle. This trick has been used to learn more about nuclear physics, condensed matter physics, and even the mysterious nature of black holes. After Maldacena introduced the idea, other physicists like Stephen Gubser, Igor Klebanov, Alexander Polyakov, and Edward Witten helped develop it further. By the year 2015, Maldacena's original paper had been cited over 10,000 times, making it one of the most important papers in modern theoretical physics. The concept of entropy also helps us understand black holes better. A system with high entropy, like hot gas, is extremely random and unpredictable at the microscopic level. On the other hand, something like an electric or magnetic field, which we can describe very precisely, has zero entropy because there's nothing random about it. For a long time, scientists thought black holes, which are perfect solutions to Einstein's equations, had no entropy either. They seemed too perfect, too orderly. But a physicist named Jacob Bekenstein realized there was a serious problem. According to one of the most important rules in science, called the second law of thermodynamics, the total amount of disorder or entropy in the universe should always increase or at least stay the same. However, if you throw something like hot gas, which has a lot of entropy, into a black hole, all that disorder seems to vanish. Once the gas crosses the black hole's event horizon, the invisible boundary around it, there's no way to see what the gas was like before. The black hole just swallows it up, smooths everything out, and becomes calm again. That seemed to break the rule about entropy always increasing. To solve this mystery, Bekenstein suggested a clever idea. What if black holes themselves have entropy? And what if, when a black hole swallows something, its own entropy increases by more than the amount it swallowed? In that case, the second law of thermodynamics would still hold true. Now, imagine we are looking at a certain volume of space. According to Bekenstein, if a black hole fills that space, it should be the thing with the most entropy possible for that size. Why? Because if you could find something else in that same space that had even more entropy, and you kept throwing matter into it, eventually it would turn into a black hole. But then the black hole would have less entropy than before, which would again break the second law. So, the black hole must be the champion of entropy for its size. Bekenstein worked out that in a sphere with a certain radius, let's call it radius r, the entropy of a hot, fast-moving gas, a relativistic gas, goes up as the energy increases. But there's a catch. If you add too much energy, gravity wins, and the gas collapses into a black hole. This gives us a natural limit. Using this idea, Bekenstein figured out that there is a maximum amount of entropy you can pack into a region of space, and that this limit depends not on the volume, but on the surface area of the space. More precisely, he concluded that a black hole's entropy is directly proportional to the area of its event horizon. Here's where things get even more fascinating. Due to a strange effect called gravitational time dilation, time itself seems to freeze at the event horizon, at least from the point of view of someone watching from far away. Because nothing can move faster than the speed of light, and because time seems to stop at the edge of a black hole, no object can actually appear to cross the event horizon from the outside. Instead, all the information about the object and its quantum properties gets stuck or imprinted on the event horizon. From this point of view, the entropy and all the hidden details of everything the black hole has swallowed are stored right on its surface. Meanwhile, another brilliant scientist, Stephen Hawking, had already shown that the total surface area of black holes always increases over time. The edge of a black hole, the horizon, is shaped by special paths of light called light-like geodesics. These are the light rays that are just barely unable to escape the black hole's gravity. If nearby geodesics begin to move toward each other, they end up inside the black hole and vanish. So only the ones that keep spreading out continue to form the horizon. That means the number of geodesics creating the horizon and the horizon's area can only grow over time. Hawking called this idea the second law of black hole thermodynamics because it reminded him of the second law of thermodynamics in regular physics. At first, Hawking didn't believe black holes were like normal thermal objects. He thought they had zero temperature because they didn't emit any radiation, and therefore couldn't be in balance with anything that had a real, positive temperature. But then, he made a shocking discovery. Black holes actually do radiate energy. This became known as Hawking radiation. In thermodynamics, when you add heat to something, its entropy increases by the amount of energy added divided by its temperature. So, if black holes had real, non-zero entropy, then they should also have a real, non-zero temperature. That would mean black holes could exchange energy with their surroundings. In other words, they wouldn't just absorb photons, particles of light. They would also need to emit them to stay in balance with the surrounding gas of photons. Now, here's where it gets really interesting. Normally, objects that don't change with time, called time-independent solutions to equations, don't emit radiation because they preserve energy exactly. Hawking wanted to use this to prove that black holes couldn't radiate. But when he did a careful calculation, he was surprised to find the opposite. black holes do radiate, and they do it in just the right way to come into equilibrium with their surroundings at a certain temperature. Thanks to this discovery, Hawking was able to calculate exactly how much entropy a black hole has. He found that the entropy is equal to 1/4 of the area of the event horizon, when measured in special natural units called Planck units. Entropy, in physics, is related to how many different ways a system can be arranged on the microscopic level without changing what it looks like on the outside. The more ways there are, the more entropy the system has. So, what Bekenstein and Hawking were saying was truly strange and fascinating. The number of hidden internal arrangements, or microstates, of a black hole is not related to the volume inside it, but only to the area of its surface. That was completely unexpected and remains one of the biggest puzzles in physics. Later on, another physicist named Raphael Bousso took Bekenstein's ideas further and came up with a new version of the entropy limit. His version was based on special surfaces called null sheets, which helped make the idea more general and apply to a wider variety of situations. Stephen Hawking once made a surprising discovery. He showed that black holes, which were once thought to trap everything forever, actually give off a faint glow of radiation. But what really shocked people was what this radiation seemed to mean. According to Hawking's calculations, the light and energy coming out of a black hole had nothing to do with what went in. In simpler words, the black hole seemed to forget what it had swallowed. Imagine a black hole like a giant cosmic vacuum cleaner. Matter and light fall in, but the light that comes out doesn't carry any information about what was sucked in. The outgoing light seems to form right at the edge of the black hole and hangs around the outer boundary, called the event horizon, for a long time. Meanwhile, the stuff falling into the black hole doesn't even reach that edge until later. The falling and escaping energy only interact for a brief moment when they cross paths. That moment isn't nearly enough to transfer all the needed information. So it's very hard to believe that the light escaping the black hole could somehow be shaped by what went in, just by a small interaction like that. Hawking believed this meant that when a black hole absorbs pure light particles, called photons, which are nicely described in quantum mechanics by a wave function, it spits out new photons that are completely different. These new photons come out in a kind of random mix, like a fog of possibilities, described not by a wave function, but by something called a density matrix. If this is true, it creates a big problem for physics, because in the rules of quantum mechanics, a neat and tidy wave, a pure state, is never supposed to turn into a random cloud, a mixed state, on its own. That would mean something is wrong or incomplete in quantum mechanics itself. This strange and troubling problem is known as the black hole information paradox, and it left many scientists scratching their heads. One of them was Gerard 't Hooft, a brilliant physicist. He looked more closely at the way Hawking radiation works. He realized that when radiation escapes a black hole, it might actually be affected by the matter falling in. Here's how. As particles fall into the black hole, their gravity could slightly bend and shape the edge of the black hole. This tiny change in the black hole's surface could, in turn, affect what kind of particles come out. According to 't Hooft, when something falls into a black hole, its gravitational pull causes a small bump, shaped like a tent pole on a flat surface, on the black hole's horizon. This bump, though small, holds important information. It's like a fingerprint, showing the mass and position of the particle that fell in. For a simple kind of black hole, one that's spherical and not electrically charged, this bump is very similar to the way particles behave in string theory, where particles are described as tiny, vibrating strings. This idea led 't Hooft to suggest that black holes might be described using the strange but powerful mathematics of string theory. All the information about particles that fall into a black hole could be stored in the small distortions on its surface, just like a hologram, where a flat surface stores all the information of a three-dimensional object. Leonard Susskind, another leading thinker, took this idea even further. He had been working on something called the holographic principle, which says that all the information in a space can be stored on its boundary, just like a hologram. Susskind believed that the changing and vibrating surface of a black hole could completely describe everything that falls in and everything that comes out. He pointed out that the way strings behave in string theory matches perfectly with this holographic idea. Small, simple strings have no entropy, which means no information loss, but big, complex strings can behave just like ordinary black holes. This showed that black holes and strings might be two sides of the same coin. Thanks to the work of these scientists, the black hole information paradox started to make more sense. If quantum gravity, the set of laws that combines quantum physics with gravity, is described using string theory, then it's possible that no information is really lost. Everything that falls into a black hole could be recorded in the tiny vibrations of its surface. Space and time, in this view, aren't the most basic ingredients of the universe. They emerge from the way the black hole's surface moves and changes. Back in the year 1995, a physicist named Leonard Susskind, along with his colleagues Tom Banks, Willy Fischler, and Stephen Schenker, came up with a groundbreaking new idea. They introduced a version of the mysterious M theory using something called a holographic description. In this description, they used tiny, supercharged black holes known as D0 brains, tiny building blocks from a version of string theory called Type 2A string theory. Interestingly, this idea wasn't completely new. A few years earlier, Bernard de Wit, Jens Hopper, and Hermann Nicolai had already proposed something similar. They thought that if you looked at two special objects called brains in 11-dimensional supergravity, a kind of high-level theory combining gravity with other forces, you could describe them using matrices, basically grids of numbers that can describe complicated systems. Later, this matrix model was reinterpreted. Instead of just describing brains, it could also explain how these tiny black holes behave under certain conditions. Thanks to the holographic principle, Susskind and his team realized something amazing. The way these small black holes move and interact might actually describe all of M theory, even in its most complex form. This was a big deal because it offered a non-perturbative version of the theory, which means it could handle all situations, not just small changes or simple cases. Then, in 1997, a physicist named Juan Maldacena took things even further. He gave the first real example of a holographic description for a more complex object, a four-dimensional object called the Type 2B membrane. This was important because it finally solved a long-standing mystery in physics, how to describe certain gauge theories, which are used to explain forces like electromagnetism and the strong nuclear force, using string theory. His work also showed deep connections between string theory and special kinds of quantum field theories that include something called supersymmetry. Now, let's talk about something called information entropy. This is a concept from physics that describes how much uncertainty or randomness is in a system. The more possible microscopic arrangements, or microstates, a system has, the more information it contains. To measure this, physicists take the logarithm of the inverse of the chance that a system is in a certain state. This is basically a fancy way to say the less likely a state is, the more information it carries. When you calculate the average information content over all possible states, you get something called the entropy of the system. This idea lines up with Gibbs entropy, which has been used in classical physics for over a century. Applying this idea to the real world leads to a fascinating conclusion. If you take a certain amount of energy in a certain volume of space, there's actually a limit to how much information that space can hold. This is known as the Bekenstein bound. If you try to cram in more information than this limit allows, the space will collapse into a black hole. That means there's a maximum amount of information or detail you can have about all the tiny particles in that space. This also tells us something deep about matter itself. It suggests that you can't keep breaking down particles into smaller and smaller pieces forever. There must be a final, fundamental level, like the ultimate Lego bricks of the universe. Why? Because if a particle had an endless number of subparticles, the number of ways it could behave, its degrees of freedom, would also be infinite. But this would go against the entropy limit we just talked about. So the holographic principle tells us that there's a stopping point, an end to how deeply you can divide matter. The most solid and detailed version of this principle is something called the ADS-CFT correspondence, which was introduced by Juan Maldacena. It shows a precise connection between two different kinds of theories, one that works in a curved space called anti-de Sitter space, and another that lives on the boundary of that space and behaves like a conformal field theory. But even earlier, in the year 1986, physicists J. David Brown and Mark Heno had discovered something similar. They showed that the symmetry of three-dimensional gravity, with two spatial dimensions and one time dimension, leads to a mathematical structure called the Virasoro algebra, which plays a big role in two-dimensional conformal field theories. Fuzzballs are an unusual and imaginative idea that comes from a theory called superstring theory. Scientists created this idea to help explain black holes in a way that works with both quantum physics and Einstein's theory of general relativity. Normally, black holes are described as mysterious objects where gravity is so strong that nothing, not even light, can escape. But fuzzballs offer a new picture. Instead of having a scary, infinitely dense point in the center, they might actually be giant balls made up of tiny, vibrating strings. Let's break it down. In string theory, the smallest parts of the universe, things even smaller than atoms, are not particles, but rather tiny loops or strands of energy called strings. These strings wiggle and vibrate in many ways, and how they move determines what kind of matter or energy they create. These vibrations happen not just in the three dimensions we can see, but also in several hidden dimensions that are curled up so small we can't detect them. Now, according to the fuzzball idea, instead of having a tiny, mysterious point called a singularity at their center, black holes are actually made up entirely of these strings. The whole inside of the black hole, up to the event horizon, the point beyond which nothing can escape, is filled with a tangled ball of these strings. That's why they're called fuzzballs, because from a distance they'd look like a fuzzy ball instead of a smooth, invisible sphere. This new view solves two big problems that have puzzled scientists for a long time. First, it gets rid of the singularity, the point where all the mass of a black hole is said to be crushed into a space with no volume and infinite density. According to Einstein's general relativity, the laws of physics break down at that point. But many physicists think the singularity isn't real. It's just a sign that our current theories are incomplete. Fuzzballs help fix this by replacing the singularity with something more physical and understandable, a dense ball of vibrating strings. The second problem fuzzballs solve is called the black hole information paradox. In simple terms, this paradox asks, what happens to all the information about matter and energy that falls into a black hole? According to quantum physics, that information can't just disappear, but classic black hole theory says it does, especially when the black hole eventually evaporates through something called Hawking radiation. Fuzzballs provide a way to keep the information safe, stored in the structure of the strings that make up the fuzzball's surface. Of course, there's a catch. We haven't yet found any direct evidence that fuzzballs, or even string theory itself, are real. All of this comes from mathematical ideas and calculations. Still, some scientists believe we might be able to test the fuzzball idea in the future using gravitational wave detectors, which pick up tiny ripples in space caused by cosmic events like black hole collisions. One of the key scientists behind the fuzzball theory is Samir D. Mathur, who works at Ohio State University. Between the years 2001 and 2012, he published 8 scientific papers on the topic. He was helped by a researcher named Oleg Lunin, who co-authored the first two papers. Together, they described black holes not as empty space with a point of doom in the middle, but as full, sphere-like objects made of strings. This is very different from the traditional idea of a black hole being just empty space with all its mass squeezed into a point. In all versions of string theory, these tiny strings are said to make up not just particles like electrons and quarks, but also the particles that carry forces, like photons for light and gluons for the strong nuclear force. The fuzzball idea comes from a particular version of string theory known as type 2IB. In this version, strings can be either open, with two ends, or closed, forming loops, and space is believed to have 9 dimensions of space and 1 of time. Out of those 9, 6 extra dimensions are thought to be folded up so tightly we don't notice them. Interestingly, a small fuzzball would look a bit like a super-dense neutron star, one of the densest things in the universe, except even more extreme. In this view, the particles inside the neutron star break apart into their smallest components, called quarks, and then transform into strings. This transformation makes the fuzzball the final stage in the life of super-compressed matter. Mather's calculations showed that the surface of a fuzzball lies right where the event horizon would be in a classic black hole. For example, the Schwarzchild radius, a fancy term for the distance from the center of a black hole to its event horizon, of a black hole with a mass of about 6.8 times that of our Sun would be about 20 kilometers, or a little over 12 miles if it isn't spinning. That's how big the fuzzball would be, but instead of being a sharp boundary, its surface would be more like a mist or a cloud, soft, fuzzy, and full of activity at the tiniest scales imaginable. In the classic view of black holes, anything that falls past the event horizon is doomed to head straight for the singularity. Space and time become so warped that nothing can escape, and everything gets crushed. But with fuzzballs, the story changes. Instead of falling into a dark and mysterious abyss, matter and light are thought to hit the fuzzy surface and get absorbed into the tangle of strings. This way, information isn't lost. It becomes part of the fuzzball itself. A fuzzball is a type of black hole, but with a big difference at the tiniest quantum level. To anyone or anything not extremely close to its surface, a fuzzball acts just like the regular black holes we know from Einstein's theory of gravity, black holes with a center point called a singularity. Light, space, and time behave around fuzzballs the same way they do around those classical black holes. The two ideas only start to disagree when we look closely at the quantum world, where the tiniest particles live. There, the fuzzball theory gives a different view of what's really going on inside. Supporters of the fuzzball idea believe this version is the true way to describe black holes when we include quantum physics. Instead of having all the matter collapse into a tiny point, a fuzzball is made up of tangled strings, the building blocks in string theory. Here's something surprising. Fuzzballs get less dense as they get bigger. This is because of something called fractional tension. When new matter or energy, which string theory calls strings, falls into a fuzzball, those strings don't just pile on top of the others. Instead, they fuse together, forming new, larger, and more complicated strings. As the strings become more complex, their tension, or tightness, gets weaker. They can stretch out and spread farther, making the fuzzball bigger but not heavier in the same way. Two scientists, Mather and Lunin, came up with a mathematical formula that describes the size of a fuzzball. Their results perfectly match the famous Schwarzchild radius, which was calculated in a totally different way by physicist Carl Schwarzchild about 87 years earlier. The Schwarzchild radius tells us how big the event horizon of a black hole should be, depending on its mass. Now, here's a fun detail. The size of a fuzzball depends on the same rule as regular black holes, the Schwarzchild radius. For a black hole that doesn't spin, that radius is about 2,953 meters for every mass equal to that of our Sun. So, As the mass of a fuzzball goes up, its size increases too, but its density drops. That's because density is the amount of mass packed into a certain volume. If you double the mass, you also double the radius, which gives you 8 times the volume. So the density becomes only 1/4 of what it was before. For example, a fuzzball that weighs 6.8 times the mass of the Sun would have an average density of around 4 times 10 to the power of 17 kilograms per cubic meter. That's incredibly dense. Just one drop of this fuzzball material, about the size of a water droplet, would weigh about 20 million metric tons. That's as heavy as a solid granite ball 243 meters wide. Even though this is unbelievably dense, it's still not close to infinite density. In fact, fuzzballs and even classical black holes are far from the maximum possible density allowed by physics, which is called the Planck density. That number is so huge, it's hard to imagine. Over 5 times 10 to the power of 96 kilograms per cubic meter, basically the weight of the entire universe squeezed into the size of an atomic nucleus. Because of the way fuzzball density decreases as mass increases, a very large fuzzball, say larger than 7 times the Sun's mass, could actually be less dense than the least dense neutron star. This means really huge fuzzballs don't need to be scary dense at all. For instance, the black hole at the center of our Milky Way galaxy, called Sagittarius A, is thought to weigh about 4.3 million times the mass of the Sun. The fuzzball model says that a non-spinning version of this object would have an average density only 51 times greater than gold. And an even larger fuzzball, say 3.9 billion solar masses, would have a radius about 77 times the distance from the Earth to the Sun, which is roughly the size of the bubble that surrounds our solar system, called the heliosphere. Its average density would then be about the same as air at sea level on Earth, about 1.2 kilograms per cubic meter. Fuzzballs and regular black holes are usually created in very violent events, such as supernovas, kilonovas, and hypernovas, which are huge explosions where stars lose a lot of their mass. But there's also a quieter way to form a fuzzball. If a neutron star slowly gains mass from a nearby star and it goes over a certain limit, it can collapse into a fuzzball or black hole without any explosion at all. Neutron stars can only hold so much mass before they collapse. This limit, called the Tolman-Oppenheimer-Volkoff limit, is not known exactly, but scientists think it's between 2.2 and 2.9 times the mass of the Sun. Once the star gets heavier than that, its own gravity overwhelms the force holding it up, and it collapses. In traditional physics, that collapse forms a black hole with an event horizon and a singularity. But in the fuzzball theory, the collapse ends differently. The particles inside the neutron star, mostly neutrons with a few protons and mesons, break down into strings, forming a ball of tangled strings. This is believed to be the true quantum version of a black hole, and maybe even the real identity of objects like quark stars, which are made of super-dense matter. Classical black holes have long posed a serious puzzle for scientists, known as the black hole information paradox. But according to a newer idea called the fuzzball theory, this mystery might not be a paradox at all. The problem first came to light in the early 1970s. In the year 1972, a physicist named Jacob Bekenstein suggested that something strange might be happening to information inside black holes. Later, the famous scientist Stephen Hawking helped bring even more attention to the issue. Here's the core of the paradox. Quantum mechanics, the science that explains the behavior of the tiniest particles in the universe, says that information about particles can never just disappear. But general relativity, the theory that explains how gravity works on a large scale, says that if black holes contain a singularity, an infinitely small and dense point, then any information that falls in is lost forever. These two ideas completely contradict each other. Quantum mechanics and general relativity are like two brilliant minds that never quite agree. One talks about the tiniest building blocks of reality, while the other focuses on giant objects like stars and galaxies. Scientists have been trying for decades to find a way to make these two theories work together. This is where fuzzball theory comes in. Based on a highly advanced framework called Type 2IB superstring theory, fuzzball theory is part of a larger idea called supergravity, which aims to describe gravity using the rules of quantum physics. Let's take a closer look at a black hole that feeds mainly on particles like protons, neutrons, and electrons that come from a nearby star. Compare that to a black hole that only swallows light, like photons from distant stars or from the cosmic microwave background. According to quantum mechanics, these two black holes should have very different internal structures because the ingredients they consumed were different. In physics, there's a basic rule. The state of something at one point in time should determine its state at any other time. But general relativity disagrees. According to this theory, once anything crosses the edge of a black hole, the event horizon, all differences vanish. Both black holes, no matter what they consumed, would only appear to grow more massive. Inside, they'd be nothing more than singularities with no size, meaning they'd have no internal structure and no way to hold on to quantum information. Even if the information somehow survived inside, it couldn't escape. The gravity near a black hole's center is so intense, not even light can get out. So how could information possibly climb back out and reveal itself? This idea is captured in something called the no-hair theorem. It says that black holes are very simple from the outside. You can only know their mass, spin, angular momentum, and electric charge. Everything else, including any information about what fell in, is lost to the outside world. Stephen Hawking added even more mystery by showing that black holes actually emit a tiny bit of radiation due to quantum effects. This is now called Hawking radiation. The strange part is that this radiation only tells us about the black hole's mass. So even though black holes glow a little bit like a hot object, they still hide nearly everything about what's inside them. But here's where fuzzball theory shakes things up. The theory, developed by physicists Samir Mathur and Oleg Lunin, says that black holes don't have a featureless center. Instead, they're made up of tangled strings, like a fuzzy ball, each one carrying quantum information. As matter falls onto the fuzzball, its strings dissolve into the fuzzball's structure. Instead of disappearing, the information becomes part of the fuzzball's complex makeup. And here's the exciting part. The fuzzball theory says that this information doesn't stay trapped forever. Some of it can tunnel through the fuzzy boundary of the fuzzball and get imprinted on Hawking radiation. That radiation then slowly carries bits of the information back into the universe, hidden as tiny patterns in the particles that escape. It's like the fuzzball whispers secrets back into the cosmos, little by little. This idea could solve the black hole information paradox because it lets quantum mechanics and general relativity finally shake hands. It offers a way to preserve quantum information even in the strangest places in the universe. Now, here's the challenge. Fuzzball theory, like the superstring theory it comes from, is entirely theoretical for now. There's no direct experiment that proves it's true. Still, it's one of the best attempts scientists have to explain how gravity works in the world of quantum physics, a problem known as finding a theory of quantum gravity. There are 5 different versions of superstring theory, including the one fuzzball theory is based on. These 5 are thought to be different pieces of an even bigger theory called M theory. None of these versions have been proven through experiments yet, but they all include quantum gravity in their descriptions. To become part of established science, like Einstein's theories of relativity, a theory must make predictions that can be tested and confirmed. Superstring theory predicts the existence of mysterious particles called superpartners. Scientists haven't found them yet, but the search continues. Fuzzball theory can't be confirmed by looking directly at Hawking radiation, because that radiation is too faint to detect with today's technology. However, there's hope it might be testable through the study of gravitational waves, ripples in space caused by the collision of massive objects like black holes. Here's another complication. Fuzzball theory is built on something called supersymmetry, which says that every particle in nature has a partner. For every known particle like a photon, a particle of light with zero mass, there is a predicted partner called a photino, a heavier particle with a different kind of spin. Likewise, electrons, which are particles with mass and a half spin, have predicted partners called selectrons that are massless and spinless, like little ghostly shadows. What makes these superpartners strange is how different they are from the particles we already know. For example, regular particles like protons and electrons can't occupy the same space because of their quantum properties, while some of their superpartners might be able to overlap more easily, like bosons do. If these superpartners exist, they could help explain why the universe is built the way it is. But until we find them, they remain purely theoretical. If scientists were able to detect superpartners, hypothetical particles predicted by supersymmetry, it would not only give strong support to superstring theory, but it would also help solve some of the big puzzles in modern physics. For example, superpartners could help explain what dark matter is made of and why the magnetic behavior of a tiny particle called the muon is slightly different from what scientists expect. According to theory, the muon's magnetic moment should be exactly equal to 2, but it's actually around 2.00233184. That tiny difference hints that there might be unknown forces or particles involved. Because of this, particle physicists have been actively searching for these superpartners. Many scientists believe that dark matter exists because of the way it affects the universe on a large scale, like how galaxies move and how the universe expands. But even though we have strong reasons to believe it's real, we still don't know exactly what it's made of. If dark matter is made of very small particles, they've proven incredibly hard to detect. Scientists have been trying to find them using different methods since the year 1986, but they've had no luck so far. This failure isn't entirely surprising. According to supersymmetry, the lightest superparticles should be stable, meaning they don't decay, have no electric charge, and interact only very weakly with regular matter. Because of these traits, they would be almost invisible to our instruments. Particle colliders, huge machines that smash particles together at high speeds, have ruled out some possible mass ranges for these particles, but the search is far from over. Another fascinating idea is called fuzzball theory, which offers a possible solution to a major disagreement between two of the most important theories in physics: general relativity and quantum mechanics. According to fuzzball theory, all the information that falls into a black hole isn't lost forever, as Stephen Hawking once thought, but instead is stored in a fuzzy, cloud-like structure called a fuzzball. The tiny bits of radiation given off by black holes, called Hawking radiation, carry this information, although in a very subtle way. These bits of radiation are thought to come from a chaotic quantum foam just above the surface of a fuzzball. The problem is that Hawking radiation is almost impossible to detect in practice. Black holes release it at extremely low energy levels. Even the individual particles of light, or photons, that make up this radiation have incredibly low energy. This explains why black holes take so long to slowly disappear or evaporate, by losing energy over time. A black hole with a mass of about 4.9 times the mass of our Sun would take 10 to the power of 59 times the current age of the universe to completely evaporate. That's a 1 followed by 59 zeros. And for a supermassive black hole weighing 106 billion times the mass of the Sun, it would take a mind-blowing 10 to the power of 90 times the age of the universe to disappear. Hawking also showed that the energy of the radiation given off by black holes depends on their size. The smaller the black hole, the more energetic the radiation it gives off. But even the smallest known black holes, like one with a mass of around 2.7 times the mass of the Sun, emit radiation made up of extremely low energy photons. This radiation would have a temperature of only about 23 billionths of a Kelvin above absolute zero, which is unimaginably cold. The total power released by such a black hole is only about 1.2 times 10 to the minus 29 watts. That's roughly 12 billion billionths of a single milliwatt. To put it in perspective, this amount of energy is to 1 watt what 1/3000th of a single drop of water is to all the oceans on Earth. And here's the really tricky part. When signals are this weak, the challenge isn't just about using better equipment. The radiation comes in the form of single photons, so a tiny black hole might only emit about 10 of them every second. Even if such a black hole were as close as 100 light-years away, the odds of even one of those photons reaching Earth and being detected by a telescope while a person is watching are extremely slim. This is especially true for the giant black holes at the centers of galaxies. Take M87, for example, which is a typical supermassive black hole. It might release only about 13 photons every 100 years, and the radiation it gives off has such a long wavelength that any detector designed to catch it would need to be larger than our entire solar system. Despite all these difficulties, fuzzball theory might still be testable using another method: gravitational waves. These are ripples in space-time caused by massive objects like black holes crashing into each other. Instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, have completely changed the way we study the universe. Since the very first detection of gravitational waves in the year 2015, an event called GW150914 caused by two black holes merging, the signals we've observed have matched the predictions of regular black hole physics. But in the year 2021, a group of scientists from Italy ran computer simulations that suggested something new. Their simulations showed that current gravitational wave detectors might be able to pick up special signs of fuzzballs. These signs would appear during the final ring-down phase after two black holes merge, sort of like the fading vibrations after a bell is struck. According to the simulations, fuzzballs would cause the vibrations to fade more slowly and create unusual echoes from earlier oscillations, which wouldn't happen with normal black holes. Another Italian research team, a year earlier in 2020, suggested that future observatories, like the planned Laser Interferometer Space Antenna, LISA, would be even better at spotting these effects. LISA is designed to detect gravitational waves from very large black hole mergers at much lower frequencies than current instruments can handle. If built, LISA could improve our ability to test fuzzball theory by many orders of magnitude. Primordial black holes, often called PBHs, are a type of black hole that scientists believe might have formed in the very early moments after the Big Bang, long before the first stars were born. These black holes are still only a theory, but they're fascinating because they don't follow the usual rules we see with black holes today. Normally, black holes are created when a giant star explodes in a supernova and its core collapses under gravity. But PBHs could have been formed in a very different way. During the inflationary era and the early period of the universe, when it was mostly made up of intense radiation, tiny but extremely dense pockets of matter may have been squeezed so tightly that they collapsed under their own weight, creating black holes without any stars involved. Since these primordial black holes would have been created before stars even existed, they wouldn't be limited to the same mass range as regular stellar black holes, which usually weigh a few times more than our Sun. This means PBHs could come in a much wider variety of sizes. The idea of primordial black holes was first suggested in the year 1966 by two Soviet scientists, Yakov Zeldovich and Igor Novikov. A few years later, in 1971, Stephen Hawking carried out the first deep study of this idea. Even today, however, these black holes remain just a theory. No one has found direct proof that they exist. In September of the year 2022, a team of scientists proposed that these early black holes might help explain a strange discovery made by the James Webb Space Telescope. It had spotted enormous galaxies that seemed to exist far earlier in the universe than expected. PBHs could have played a role in helping those giant galaxies form so quickly. For a long time, PBHs have also been thought of as a possible explanation for dark matter, the mysterious substance that makes up most of the matter in the universe but doesn't emit any light. In fact, some researchers believe PBHs could make up nearly all of the dark matter. Support for this idea has grown thanks to observations from the LIGO and Virgo detectors, which detect gravitational waves, and from the James Webb Space Telescope. Early theories about PBHs often assumed they would all be roughly the same size. But this idea, called a monochromatic mass distribution, was challenged by the LIGO and Virgo results. These showed that black holes come in a variety of sizes, not just one. More recent data from the James Webb Telescope supports the idea that black holes could have a wide range of masses, possibly centered around one solar mass, about the same weight as our Sun. Some PBHs might be as small as an asteroid, but with a mass squeezed into the size of a hydrogen atom. These tiny black holes could be zipping through space at incredible speeds. In fact, it's possible that one of them might be somewhere within our own solar system right now. Most of the time, if one passed through a star, it would just go straight through without causing any harm, like a bullet through fog. But if it moved slowly enough, there's a small chance it could get caught by the star's gravity. Stephen Hawking even suggested that our own Sun might be hiding one of these tiny black holes. Depending on the theory, a PBH could have started with a mass as small as 10 to the -8th kilograms, which are sometimes called Planck relics, all the way up to thousands of times the mass of our Sun. However, PBHs that were originally lighter than 100 billion kilograms probably wouldn't exist anymore. They would have disappeared due to a strange process called Hawking radiation, which slowly makes small black holes evaporate over time. Because of this, only the heavier PBHs would still be around today. Primordial black holes don't contain the kind of matter that makes up stars, planets, and people. They're made of non-baryonic matter, which is another reason scientists think they could be responsible for dark matter. Some researchers also believe that these early black holes might have been the seeds that helped form the gigantic black holes found at the centers of large galaxies, or even the intermediate-sized black holes found in smaller galaxies. PBHs fall into a broader category of objects known as massive compact halo objects, or MACOs. These objects are great candidates for dark matter because they don't interact much with other matter. They are stable if they're big enough, and they move slowly through space. Importantly, they also would have formed very early in the life of the universe, within 1 second after the Big Bang. Still, not everyone agrees. Some scientists point to various space observations that seem to place strict limits on how many PBHs could exist. According to them, PBHs probably don't make up most of the dark matter, but new studies suggest they could still be important, especially if they tend to gather in small clusters, with perhaps a 30 solar mass PBH sitting in the center of each cluster. In March of the year 2016, just 1 month after scientists announced they had detected gravitational waves for the first time using advanced LIGO and Virgo, 3 different research groups came forward with an idea. Maybe those waves came from 2 PBHs merging together. Each black hole had about 30 times the mass of the Sun, which was surprising. 2 of the groups said this matched what we'd expect if PBHs made up all of dark matter, as long as they were clustered inside small galactic halos like faint dwarf galaxies or globular clusters. But the 3rd group disagreed. They said the merger rate seen by LIGO was too low, and PBHs could only make up less than 1% of dark matter. The surprisingly large masses of the black holes detected by LIGO brought new attention to the idea of PBHs with masses between 1 and 100 times that of our Sun. Scientists are still debating whether this idea fits with other observations, like the lack of microlensing, a way of detecting hidden black holes, patterns in the cosmic microwave background, the size of small galaxies, and the lack of matching X-ray and radio signals near the center of our galaxy. In May of the year 2016, A scientist named Alexander Kashlinsky put forward a fascinating idea. He noticed certain patterns in background radiation, specifically in gamma rays and X-rays, that scientists hadn't fully explained yet. These patterns appeared in areas of the sky where no individual sources, like stars or galaxies, could be clearly seen. Kashlinsky suggested that these mysterious signals might actually come from primordial black holes, which are ancient black holes formed just moments after the Big Bang. He thought that if these black holes had similar masses and were as common as dark matter, they might explain the strange radiation patterns. Then, in August of the year 2019, another study opened up an even more surprising possibility. It proposed that all of the dark matter in the universe, this invisible stuff that makes up most of the mass in the cosmos, could actually be made up of primordial black holes that are about the mass of asteroids. That was a bold and exciting idea, suggesting that these tiny but incredibly dense objects might be everywhere. Just 1 month later, in September of the year 2019, researchers James Unwin and Jakob Scholz introduced another surprising theory. They believed that a black hole with a mass between 5 and 15 times the mass of Earth might be hiding far away in our own solar system, in a region beyond Neptune known as the Kuiper Belt. Strangely, this black hole would be about the size of a tennis ball, but extremely heavy. Their idea came from noticing that some distant objects in space were moving in odd ways, as if something massive and invisible was pulling on them. This mysterious object might be what some people have been calling Planet 9, but instead of a planet, it could be a primordial black hole. In October of the same year, two scientists named Derek Inman and Yassine Ali Haimoud studied how the universe's structure formed and whether this could affect our measurements of the cosmic microwave background, CMB, the leftover radiation from the Big Bang. They found that the small movements caused by this structure formation weren't strong enough to change what we already know from the CMB. So, any constraints scientists were using to study black holes and the early universe still held up. Fast forward to September of the year 2021, when a group of researchers from the Nanograv collaboration made an exciting announcement. They had detected a low-frequency signal that might be coming from gravitational waves, ripples in space and time. Some scientists thought this signal could be linked to primordial black holes, giving a possible new way to detect them indirectly. In September of the following year, 2022, scientists once again turned their attention to primordial black holes to explain something new. The James Webb Space Telescope, one of the most powerful space observatories ever built, had spotted enormous galaxies that seemed to have formed way too early in the universe's history. These ancient, massive galaxies didn't quite fit with existing models, but if primordial black holes had helped galaxies form faster and earlier than expected, it could explain these strange discoveries. Then, on the 26th of November, 2023, something truly remarkable was reported. For the first time ever, astronomers found strong evidence for what they called an overmassive black hole galaxy, or OBG. This type of galaxy may have formed through a rare process known as direct collapse, where a black hole is born directly from a massive cloud of gas, not from the death of a star, which is the usual way black holes are formed. This discovery came from studying a distant early galaxy called UHZ1, which contains a powerful quasar, a super bright object powered by a black hole, using both the Chandra X-ray Observatory and the James Webb Space Telescope. In the year 2024, a review led by physicist Bernard Carr and his colleagues looked into the origins of primordial black holes. They concluded that these black holes might have been created during a moment called the quantum chromodynamics epoch, which occurred less than 100,000th of a second after the Big Bang. The team also found that the sizes, or masses, of these black holes today would follow a special pattern with several noticeable bumps, one of which is around 1 solar mass, about the same mass as our Sun. So, how do primordial black holes even form in the first place? Scientists believe that they could have appeared in the very first second after the Big Bang, either during the mysterious inflationary era or early on during the radiation-dominated era of the universe. For a black hole to form, there has to be a dense region in space where gravity becomes so strong that the matter collapses in on itself. These regions might come from density fluctuations, tiny differences in how matter was spread out in the early universe. There are a few ways such fluctuations might have been created. One idea is axion inflation, a theory in which a strange particle called an axion behaves like a field during inflation, causing the energy in space to wobble and ripple. These ripples might have created the seeds for future black holes. Another possible cause is reheating, a brief period that came right after inflation ended. During reheating, the inflaton field, a field thought to drive inflation, broke down into particles. These particles started bumping into each other, trying to reach thermal equilibrium. But if this process didn't happen smoothly, it might have left behind uneven patches of matter that later collapsed into black holes. A third explanation involves cosmological phase transitions, moments when the universe changed states, like water freezing into ice. These transitions might have created dense regions or released energetic particles that collapsed under their own gravity. Now let's return to the dark matter mystery, a puzzle first proposed back in 1933 by the Swiss-American astronomer Fritz Zwicky. Scientists have long known that galaxies and clusters behave as if there is far more matter present than what we can see. The idea is that there must be some invisible material, dark matter, that adds extra gravity. Primordial black holes might help solve this mystery. First, if there are enough of them, they could make up all or most of the dark matter in the universe. Second, unlike some of the other dark matter candidates like WIMPs, weakly interacting massive particles, primordial black holes can give off gravitational waves, which interact with regular matter and can be detected with modern instruments. Lastly, these black holes might explain strange effects of gravitational lensing, where light from distant stars gets bent in odd ways, something that regular matter can't fully explain. Although scientists haven't yet proven that primordial black holes are the true identity of dark matter, the evidence keeps building. Researchers like Bernard Carr and others continue to explore this idea, believing that the answer might lie in the very first moments of the universe itself. Primordial black holes, often called PBHs, are very special because unlike regular black holes that form from dying stars, they could have been born just moments after the Big Bang. What makes them even more fascinating is that they don't have to be tiny. They can come in all kinds of sizes. Because of this, scientists believe that PBHs might have played a major role in the birth of galaxies, including some that formed earlier than scientists once thought possible. Back in the year 1974, a brilliant Soviet physicist named Yakov Zeldovich came up with an interesting problem in cosmology. He called it the cosmological domain wall problem. He suggested that when the early universe went through its rapid changes, known as phase transitions, it might have created invisible boundaries called domain walls. These walls would have carried an enormous amount of energy, and if too many had formed, they could have messed up the universe as we know it. But PBHs might offer a clever solution to this problem. There are a few ways PBHs could help solve the domain wall issue. First, if PBHs formed early enough, their powerful gravity could have pulled matter around them into clumps. This clumping might have stopped the domain walls from forming in the first place. Second, if domain walls had already formed, PBHs could have helped destroy them. Their strong gravitational pull might have caused these walls to collapse and eventually form more PBHs. Third, PBHs might simply not interfere with what we see in the universe today. For example, if we were to find PBHs with masses between 10 to the power of 12 and 10 to the power of 13 kilograms, that would be just the right amount to explain all the dark matter in the universe without causing any problems or breaking any observational rules. But that's not all. Yakov Zeldovich also proposed another big mystery in the late 1970s, known as the cosmological monopole problem. Magnetic monopoles are strange, hypothetical particles that carry only one magnetic pole, unlike magnets we know, which always have a north and south pole. According to some theories, these monopoles should have formed in the early universe, but oddly enough, we don't see them today. PBHs might also help explain where these magnetic monopoles went. Here's how. One idea is that if magnetic monopoles did exist in the early universe, they might have been pulled into and swallowed by PBHs due to their gravity. Another idea is that PBHs might have caused matter to gather in clumps, which would have spread the magnetic monopoles out so thinly that they're nearly impossible to detect today. There's another curious twist in this story involving something from string theory, a highly advanced idea in physics. According to general relativity, the smallest PBH should have evaporated by now, disappearing over time due to a process called Hawking radiation. But if there's actually a fourth dimension of space, as string theory suggests, then gravity could behave differently on small scales. This extra dimension might slow down the evaporation of tiny PBHs, letting them survive much longer. In simple terms, energy from that hidden dimension could act like extra mass in our regular space, keeping small PBHs from disappearing too quickly. If this theory is right, there could be thousands of tiny PBHs scattered across our Milky Way galaxy. To test this idea, scientists are using a special instrument called the Fermi Gamma Ray Space Telescope, launched by NASA on June 11, 2008. If it sees certain patterns in bursts of gamma rays, like tiny ripples, it might be the first clue that both PBHs and the hidden dimensions predicted by string theory are real. Scientists have also tried to figure out how many PBHs might exist and how massive they could be based on what we can observe. One method is by studying Hawking radiation, the process that Stephen Hawking proposed in 1974. He believed that small PBHs could be floating around in the halo, the outer part, of our galaxy. All black holes are thought to slowly lose mass by emitting Hawking radiation, and the smaller they are, the faster they lose mass. When a black hole gets really small, it could explode in a final flash of energy, like a massive hydrogen bomb releasing millions of megatons of force. A regular black hole, like one with 3 times the mass of our Sun, would take an unimaginable amount of time, around 10 to the power of 69 years, to completely vanish. That's far longer than the current age of the universe. But PBHs might be much smaller, and a PBH with a mass of about 10 to the power of 11 kilograms would have a lifetime roughly equal to how long the universe has existed so far. If enough of these formed in the Big Bang, we might see some of them exploding nearby in our galaxy even today. NASA's Fermi telescope, which went into orbit in June 2008, was partly designed to look for such events. Based on what it has seen, scientists now believe that no more than 1% of dark matter can be made up of PBHs with masses up to 10 to the power of 13 kilograms. Also, if PBHs had existed in large numbers back then, their radiation would have changed the amounts of light elements, like hydrogen and helium, formed in the early universe. But here's the tricky part. If Hawking radiation turns out not to be real, then PBHs would be extremely hard to find. Because they're so small and don't have much gravity compared to bigger black holes, they would remain nearly invisible in space. In the early days of the universe, tiny black holes called primordial black holes might have formed. These black holes could have sucked in surrounding matter, releasing energy into the space around them. This energy would have affected a very important event in the history of the universe called recombination, which happened when the universe cooled down enough for atoms to form. When we study the light left over from the Big Bang, known as the cosmic microwave background or CMB, we can look for signs of this energy injection. The CMB has tiny temperature differences called anisotropies spread across the sky. These differences can be measured with great precision. The Planck satellite, which observed the CMB in amazing detail, has shown that primordial black holes with masses between 100 and 10,000 times the mass of our Sun probably cannot make up a big part of the mysterious dark matter, at least according to the simplest theories. However, scientists are still debating whether these rules might change under more complex or realistic models. Another exciting idea is that dark matter, the invisible stuff that makes up most of the matter in the universe, might be made of particles called WIMPs, short for weakly interacting massive particles. If primordial black holes gathered a cloud or halo of these WIMPs around them, then the WIMPs could crash into each other and annihilate, releasing high-energy light known as gamma rays. Instruments like the Fermi Gamma Ray Space Telescope are specially designed to look for this kind of light and might one day spot it. In the coming years, several powerful instruments and experiments will help scientists look for signs of primordial black holes in new and exciting ways. The Square Kilometre Array, SKA. This giant radio telescope will study how primordial black holes may have affected the period when the first stars and galaxies formed. If these black holes released energy by pulling in matter, they could have changed the history of how the universe became ionized again. Gravitational wave detectors like LIGO and Virgo. These devices have already found black holes crashing into each other. If they detect black holes with masses below 1.4 times the Sun's mass, it could be a strong clue that those black holes are primordial, not the result of dying stars. They can also tell if the orbits of these black holes are unusually eccentric, another potential sign of primordial origins. LISA, Laser Interferometer Space Antenna, and pulsar timing arrays will look for faint background ripples in spacetime, made by primordial black holes orbiting each other long before they merge. Faint dwarf galaxies and their star clusters. Some small, dark, matter-heavy galaxies might hold lots of primordial black holes. Studying their central regions could offer clues. Tracking stars in our own Milky Way. If a primordial black hole is nearby, it might subtly change the motion of stars around it, something we could detect. Listening for sound waves. It has even been suggested that if a small black hole passed through the Earth, it would make a unique sound-like signal. Because these black holes are tiny but incredibly heavy and fast, they would shoot through the Earth without causing damage, just a few tiny interactions with atoms. Watching for starquakes. If a primordial black hole passed through a star, its powerful gravity might make the star ripple or vibrate. Scientists could spot these changes. Microlensing effects. When black holes pass in front of distant stars or quasars, they can bend the light with their gravity. By looking at microwave light from quasars and the way it bends, scientists might spot the hidden presence of primordial black holes. Tracking planets. A fast-moving primordial black hole zipping through the solar system might tug slightly on planets like Mars. This could be detected as a small but sudden change in their paths. Although none of these tools are designed specifically to find primordial black holes, each one offers a piece of the puzzle. Together, they help scientists gather indirect clues and test different ideas about what primordial black holes might be like. LIGO and Virgo. These detectors have already helped set limits on how common primordial black holes might be. If they detect black holes with masses that don't match what we expect from regular star deaths, that could point to something more exotic, like PBHs, Cosmic Explorer, and the Einstein Telescope. These are future upgrades to LIGO and Virgo. They will be more sensitive and will be able to detect gravitational waves from farther back in time, which means better chances of spotting signs of PBHs. Nanograv. This project recently found a mysterious signal, which might turn out to be gravitational waves. If confirmed, and if it turns out to come from black holes smaller than the Sun, that could be evidence for PBHs. LISA. This future space-based detector will be able to pick up signals from extreme mass ratio in spirals, cases where a small black hole spirals into a much larger one. This would be another way to spot PBHs. It may also confirm signals like the one nanograv saw. EDGE, atomic experiment for dark matter and gravity exploration in space. This experiment, still in the planning stage, will try to catch signs of medium-sized black holes merging, something that could help prove PBHs helped form supermassive black holes in the early universe. Nancy Grace Roman Space Telescope, formerly WF-1. This space telescope will help detect PBHs through a method called astrometric lensing, where the position of a star shifts slightly when a dark object passes in front of it. Vera C. Rubin Observatory, LSST. This ground-based observatory will look for brief flashes of light caused by microlensing, helping measure the masses of compact objects and spot strange ones that might be PBHs. It could even detect special types of cosmic explosions called colonovae that might hint at the presence of PBHs. NGVLA, Next Generation Very Large Array. This powerful radio telescope will help improve on the nanograv results and distinguish between different sources of gravitational wave signals, helping confirm or rule out PBHs. Fast radio bursts, FRBs. These mysterious bursts of radio waves could help too. If a PBH passes between Earth and the FRB source, it could create a lensing effect. Studying many FRBs could reveal patterns caused by PBHs. There is still an unexplored area of the gamma-ray spectrum called the MEV band. If scientists build detectors to observe it, they could place tighter limits on how many asteroid mass PBHs exist. Primordial black holes with a mass around 5 × 10 to the power of 19 grams, about the mass of a large asteroid, would be emitting powerful TeV gamma rays as they slowly evaporate. These emissions would show up as random bursts all over the sky. Wide-field telescopes would be perfect for catching them, even if they don't cover large areas of the sky at once. These telescopes are very sensitive and could place upper limits on how often these bursts happen. Not all black holes form the same way. Some are direct collapse black holes, formed from the collapse of massive gas clouds after the era dominated by radiation. But primordial black holes are different. They could have formed much earlier, during the first split second after the Big Bang, from collapsing energy and particles. As scientists continue exploring the universe with better tools, they might finally find out whether these mysterious ancient black holes really exist and what secrets they might hold. A stellar black hole, also known as a stellar mass black hole, is born when a massive star reaches the end of its life and collapses under its own gravity. This dramatic event is called a gravitational collapse, and it creates one of the most mysterious and powerful objects in the universe, a black hole. These black holes usually have masses between 5 and several dozen times the mass of our Sun. Stellar black holes are the remains of giant stars that exploded in an extremely violent event known as a supernova. Sometimes these supernovae can be seen as bright flashes of gamma rays, the most energetic form of light. Because of the way they form, these black holes are also sometimes called collapsers, which is short for collapsed stars. According to an important idea in physics called the no-hair theorem, a black hole is surprisingly simple. No matter how it formed, it can only be described by 3 basic features: its mass, how much stuff it contains, its electric charge, and its angular momentum, which has to do with how fast it spins. A stellar black hole spins because the star it came from was also spinning, and that rotation gets passed on when the star collapses. The process of forming a black hole is actually a natural part of a star's life cycle. When a really massive star runs out of fuel, it can no longer produce the energy it needs to support itself. At this point, gravity takes over, and the core of the star begins to shrink. If the remaining core is not too massive, it might become a white dwarf or a neutron star, depending on its weight. These are extremely dense, compact objects. In very rare cases, some scientists think it could even become a quark star, which is a still theoretical type of star made of tiny particles called quarks. But if the core is too heavy, it crosses a point of no return known as the Tolman-Oppenheimer-Volkoff (TOV) limit. If the collapsing material has a mass greater than this limit, nothing can stop the collapse. The star continues shrinking until it becomes infinitely small, creating a black hole, a point in space where gravity is so strong that nothing, not even light, can escape. Back in the year 1939, scientists estimated the TOV limit to be around 0.7 times the mass of the Sun. However, later studies, like one from 1996, revised this estimate to be somewhere between 1.5 and 3 times the mass of the Sun. The heaviest known neutron star discovered so far is called PSR J0740+6620, found in September of 2019, and it has a mass of about 2.14 times the mass of the Sun. According to Einstein's theory of general relativity, black holes can, in theory, have any mass at all. But the smaller the black hole, the denser the matter needs to be to create it. However, in the real universe, no known stars can collapse to form black holes smaller than a few times the Sun's mass. If very small black holes do exist, they probably formed shortly after the Big Bang and are called primordial black holes. Until the year 2016, the biggest stellar black hole known had a mass of about 15 2/3 times the mass of the Sun. Then, in September of 2015, scientists detected gravitational waves, ripples in spacetime, from the merger of two smaller black holes. The resulting black hole was spinning and had a mass of about 62 times the mass of the Sun. In June of 2020, scientists announced the discovery of what was, at the time, the smallest known stellar black hole. It is located in a binary star system called 2-mass J 05 2 1 5 6 5 8 plus 4 3 5 9 2 2 0. This tiny black hole has a mass of just 3.3 times the mass of the Sun, and its diameter is only about 19.5 kilometers. That's smaller than many cities on Earth. Besides stellar black holes, astronomers have also found evidence for two other types of black holes. One kind, called intermediate mass black holes, may exist in the centers of globular clusters, large groups of stars. The other type is the supermassive black hole, which lies at the heart of galaxies, including our own Milky Way. These giants are millions or even billions of times more massive than the Sun. Sometimes, stellar black holes live in close partnerships with a regular star in a binary system. In these cases, the black hole can pull matter from its companion star. As this matter falls toward the black hole, it speeds up and gets so hot, reaching temperatures of hundreds of millions of degrees, that it begins to emit X-rays. These X-rays can be detected with special telescopes, allowing scientists to see the otherwise invisible black hole. The companion star, meanwhile, can be seen with ordinary optical telescopes. Interestingly, black holes and neutron stars can sometimes be hard to tell apart because they give off similar amounts of energy. Scientists figure out which is which by measuring the mass of these objects. So far, all known neutron stars weigh less than 3 times the mass of the Sun. If a compact object is heavier than that and doesn't behave like a neutron star, it's almost certainly a black hole. However, it's important to remember that most of our proof for the existence of stellar black holes comes from combining observations with theoretical physics. We haven't seen one directly. But based on everything we know, no other kind of object can explain these massive, compact sources of X-rays and gravity. A truly direct proof would be seeing something, like a particle or a cloud of gas, spiral into a black hole and disappear. Some binaries, which are pairs of stars or objects in space, have been found at much greater distances from the galactic plane than expected. This happens because of natal kicks from black holes, which are strong movements caused when a black hole forms. The way black hole natal kicks push black holes seems to be similar to the way neutron stars are kicked, even though black holes are much heavier than neutron stars. One might think that, because of their higher mass, black holes would receive lower speeds than neutron stars, but this isn't what we observe. The reason for this could be the way matter, which is ejected in an uneven manner during the black hole's formation, falls back onto the black hole and boosts its momentum. Some models of how stars evolve suggest that black holes with certain masses cannot directly form from the collapse of a star. These mass ranges are called the lower and upper mass gaps. The lower mass gap covers black holes with masses between 2 and 5 times the mass of our Sun, while the upper mass gap refers to black holes that are roughly between 50 and 150 times the Sun's mass. Another estimate for the upper gap ranges from 52 to 133 times the mass of the Sun. It's believed that the upper limit for star masses today is 150 times the Sun's mass. Scientists suspect there may be a lower mass gap because there aren't many observed black holes that are just a few solar masses heavier than the maximum mass of a neutron star. However, the idea of this gap is still uncertain. Some of the black holes in this range might not have formed from collapsing stars, but could instead have been created by the merging of 2 neutron stars. The LIGO-Virgo collaboration, which studies gravitational waves, has found 3 events where the masses of the components fit within this lower mass gap. There's also an observation of a large, rapidly spinning star in a binary system with a hidden companion. This companion doesn't give off light, including X-rays, but it seems to have a mass of about 3.3 times the mass of the Sun. This suggests there may be many low-mass black holes that are currently not pulling in material, and so they are invisible to traditional methods of detection, which rely on X-ray emissions. The upper mass gap comes from detailed models of how stars change as they age. According to these models, when supermassive stars get too heavy, they can experience a pair instability supernova. In this event, the high-energy collision between atomic nuclei and gamma rays causes the star to lose pressure in its core, which prevents it from holding up against gravity. As a result, the core partially collapses and triggers a massive explosion, completely blowing the star apart without leaving any remnant. This kind of explosion can only happen in stars that are between about 130 and 250 times the mass of the Sun and have a low amount of elements other than hydrogen and helium. This situation is common in the first generation of stars, known as population 3 stars. Some theories suggest that this mass gap could be smaller, reaching down to 45 times the mass of the Sun, due to a process called pair instability pulsational mass loss. This occurs before the star goes through a typical supernova explosion. In stars that don't rotate, the lower limit of the upper mass gap might be as high as 60 times the mass of the Sun. There is also speculation that stars with very heavy cores, above 133 times the mass of the Sun, could collapse directly into black holes without going through a typical supernova. However, there is little chance of seeing a supernova remnant from such massive stars, which means that the lower boundary of the upper mass gap may actually mark the limit for black hole formation. At one point, observations of the LB1 star system suggested the presence of a black hole with a mass of about 70 times the mass of the Sun, which would fall outside the upper mass gap. However, further research has cast doubt on this initial finding. Black holes might also be found in the mass gap through other processes, such as when 2 black holes merge. Our Milky Way galaxy contains several candidates for stellar mass black holes, which are much closer to us than the supermassive black hole at the center of the galaxy. Most of these candidates are part of X-ray binary systems, where a black hole pulls matter from its companion star, forming an accretion disk. The black holes in these systems are estimated to have masses ranging from 3 to more than 12 times the mass of the Sun. Supermassive black holes are the biggest kind of black holes we know about. These cosmic giants can weigh as much as hundreds of thousands or even millions to billions of times more than our Sun. To get an idea of just how massive that is, Imagine squeezing the weight of millions or billions of suns into a space much smaller than a galaxy. That's a supermassive black hole. Black holes themselves are mysterious and powerful objects. They form when a large amount of matter collapses under its own gravity. This collapse creates a region in space where the gravity is so strong that nothing, not even light, can escape from it. Because of this, black holes appear completely black. We can't see them directly, but we can detect their presence by how they affect nearby stars, gas, and light. Scientists have found strong evidence that almost every large galaxy in the universe has a supermassive black hole sitting at its center. Our very own galaxy, the Milky Way, has one too. It's located at the core and is known as Sagittarius A star. This black hole doesn't give off light by itself, but we can observe the energy that is produced when gas and dust fall into it. When matter from space, like gas and dust, gets pulled into these supermassive black holes, it spins around and heats up. This process releases a huge amount of energy and can create extremely bright regions called active galactic nuclei, or quasars. These powerful lights can shine brighter than the entire galaxy around them. Thanks to a network of powerful telescopes known as the Event Horizon Telescope, scientists have actually managed to capture images of two supermassive black holes. One is in a giant galaxy called Messier 87, and the other is the one at the center of the Milky Way, Sagittarius A star. To be considered a supermassive black hole, an object needs to be at least 100,000 times more massive than our Sun. But many of these giants weigh far more. Some are even several billion times heavier than the Sun. One strange and surprising fact about these black holes is that they are not as dense as you might think. In fact, if you spread the mass of a supermassive black hole across the space inside its event horizon, the boundary around a black hole beyond which nothing can return, the average density could be lower than that of water. That's because as the mass increases, the size of the black hole grows even more quickly, so the mass gets spread out over a larger volume, making the overall density lower. Here's another amazing comparison. A non-spinning, uncharged black hole with a mass of about 1 billion suns would have an event horizon nearly as wide as the orbit of Uranus, the seventh planet from the Sun. That's about 19 times the distance from Earth to the Sun. Some black holes are so huge that scientists give them a special name: ultramassive black holes. These are even larger than supermassive black holes and weigh more than 5 billion suns. Examples might include the black holes at the centers of galaxies like TON 618, NGC 1666, ESO 444, 46, and NGC 4889. These are among the heaviest black holes known to science. Most researchers believe there's a natural limit to how big black holes can grow, probably somewhere around 50 billion solar masses. But in the year 2020, a new study suggested that even larger ones could exist. These would be so enormous that scientists gave them a dramatic name: stupendously large black holes, or slabs for short. These could be more than 100 billion times the mass of the Sun. One possible example might be the black hole at the center of a galaxy cluster called Phoenix A. The story of how scientists first discovered these gigantic black holes is just as fascinating. In the year 1963, an astronomer named Martin Schmidt was studying a strange object called 3C273. At first, people thought it was just a star, but when Schmidt looked closely at its light spectrum, he realized something unusual. The light showed signs of redshift, which means the object was moving away from Earth very fast. According to Hubble's law, this meant it must be extremely far away, billions of light years from Earth. And yet, it was giving off as much energy as hundreds of galaxies combined. This object, and others like it, became known as quasars. By the year 1964, scientists had found 4 of them. These objects were incredibly bright and compact, less than about 3 light-years across, which meant something extremely powerful had to be producing that energy. To explain these strange objects, 2 scientists, Fred Hoyle and W.A. Fowler proposed the idea of supermassive stars in the early 1960s. These stars, they thought, could burn hydrogen at their cores and give off the energy seen in quasars. They imagined these stars might weigh anywhere from 100,000 to 1 billion suns. But there was a problem. The famous physicist Richard Feynman pointed out that stars above a certain size would be unstable and would collapse into black holes unless something else held them up. Fowler later suggested that such stars might go through cycles of collapse and explosion, which could explain their bursts of energy. In 1972, scientists Appenzeller and Fricker created computer models of these massive stars and found that even after trying to burn their hydrogen fuel, the stars would still collapse. In one of their models, a star 750,000 times the mass of the Sun ended up becoming a black hole anyway. Back in the year 1964, two brilliant scientists named Edwin E. Salpeter and Yakov Zeldovich had a bold idea. They suggested that the incredible energy and brightness seen in mysterious space objects called quasars might be caused by matter falling into a very massive, dense object, what we now understand as a black hole. To produce that much power, they estimated that the object would need to be about 100 million times more massive than our Sun. Then, in 1969, another scientist named Donald Lynden Bell added something important. He explained that as gas falls toward this massive object, it would not just fall straight in, it would spin around and flatten into a disk, kind of like water swirling down a drain. This spinning disk would slowly spiral into what he called the Schwarzchild throat, a term related to the event horizon of a black hole. Lynden Bell also pointed out that many nearby galaxies seem to have dim centers, which meant that they might once have been quasars, but had since gone quiet. Meanwhile, in the year 1967, Martin Ryle and Malcolm Long-Air proposed another fascinating idea. They believed that powerful radio waves coming from faraway galaxies could be explained by particles being shot out of those galaxies at speeds close to the speed of light. Later, in 1973, they worked with Peter Scheuer and suggested that the power for these super-fast jets of particles might come from the compact core at the center of each galaxy, possibly from a massive black hole. In 1970, scientists Arthur M. Wolf and Jeffrey Burbidge looked closely at elliptical galaxies, those that are round or oval in shape. They noticed that stars near the centers of these galaxies were moving around much faster than expected. The only explanation was that there must be a huge amount of unseen mass at the center, much more than could be accounted for by stars alone. They concluded that it could be one gigantic black hole as massive as 10 billion suns, or a group of many smaller black holes, each less than 1,000 times the mass of the Sun. More strong evidence came in the year 1978 when astronomers studied the elliptical galaxy called Messier 87. They found signs of a dark, massive object in the center, estimated to be 5 billion times the mass of the Sun. Soon after, similar signs were found in other galaxies too, including the Andromeda Galaxy in 1984 and the Sombrero Galaxy in 1988. Then, in 1971, Donald Lynden Bell and Martin Rees made a bold prediction. They thought the center of our own Milky Way galaxy might also contain a supermassive black hole. Just a few years later, on February 13th and 15th of 1974, astronomers Bruce Balick and Robert Brown found something exciting. Using a special radio telescope in Green Bank, they discovered a strange radio source at the center of the Milky Way. It gave off a kind of radiation called synchrotron radiation, and it didn't seem to move. Because of its strong gravity, they realized this could be the first real clue that a supermassive black hole, later named Sagittarius A, was hiding at the heart of our galaxy. Things took a giant leap forward in 1990 when the Hubble Space Telescope was launched into orbit. This powerful telescope allowed astronomers to look at the centers of galaxies with much more detail than ever before. In 1994, One of its instruments, called the Faint Object Spectrograph, observed Messier 87 again. This time, it showed that gas near the center was spinning incredibly fast, about 500 kilometers per second, around a very small area. The only explanation was a mass of nearly 2.5 billion suns packed into an area smaller than 1/4 of an arc-second across. This was some of the strongest evidence yet for a supermassive black hole. In 1995, a team led by Miyoshi used another amazing instrument called the Very Long Baseline Array to look at Messier 106. They studied radio waves from water molecules called an H2O maser and found that the signal came from a disk of gas spinning around a compact object with the mass of about 36 million suns. The space was so small, just over 1/10 of a parsec across, that a crowd of smaller black holes couldn't possibly fit without crashing into each other. So again, the only realistic explanation was a single supermassive black hole. Another big discovery around the same time was made in the galaxy MCG-6-30-15. Scientists found a special kind of X-ray signal called the iron K-alpha emission line. This signal was stretched out and distorted in a way that showed it came from very close to a black hole, just 3 to 10 times the black hole's event horizon. This confirmed how incredibly powerful and strange these objects really are. Then, on April 10th of the year 2019, something historic happened. The Event Horizon Telescope team released the very first picture of a black hole. It showed the huge black hole at the center of the galaxy, Messier 87, giving the world a glimpse of what was once purely theoretical. A year later, in March of 2020, scientists suggested that more rings of light might be found around that image, known as photon rings, which could help us understand even more about these mysterious giants. Even today, the question of where these supermassive black holes originally came from is still being studied. Scientists know they grow by pulling in gas, dust, and even other black holes. But how the very first ones, called seeds, formed is still not fully understood. Some theories suggest that they might have started from black holes that were just a few dozen or a few hundred times the mass of the Sun, created by exploding stars. Over time, these could have grown larger by feeding on surrounding material. Others think these seeds might have formed in a different way. In the early universe, before stars even existed, giant clouds of gas might have collapsed directly into something called a quasi-star, which then collapsed into a black hole about 20 times the mass of the Sun. Or maybe dark matter helped pull in huge amounts of gas, forming supermassive stars that were tens of thousands of times more massive than the Sun, which then collapsed into black holes. There's even a newer idea suggesting that right after the universe began, giant stars, each with a mass of about 100,000 suns, collapsed into black holes, becoming the seeds of the monsters we see today. Some rare theories go even further, proposing that the universe didn't begin with the Big Bang at all, but with something called the Big Bounce. If that were true, then maybe some supermassive black holes are older than the universe we live in now, having existed even before the last cosmic cycle ended. In the very early universe, huge clouds of gas floated around, far away in both space and time. These clouds were made of pure, untouched hydrogen and helium, what scientists call metal-free gas. When these clouds were hit by strong light, known as Lyman-Werner radiation, something strange happened. Instead of cooling down and breaking apart into smaller clumps, which usually leads to star formation, they stayed together. This was because the light stopped them from cooling, and gravity pulled everything inward, causing the entire cloud to collapse into a single, massive object. As this object collapsed, the pressure and density in the center became incredibly high, about 10 million grams in every cubic centimeter. That's unimaginably dense. At this point, the object could no longer hold itself together. It didn't become a star or even a quasi-star, a short-lived star-like object. Instead, it collapsed directly into a black hole. These massive objects are called direct collapse black holes, and they usually weigh about 100,000 times more than our Sun. In the year 2022, a computer simulation gave us more clues about how the very first supermassive black holes may have formed. According to this simulation, rare, chaotic clouds of gas, called primordial halos, were fed by unusually strong streams of cold gas. These cold streams kept new stars from forming too early, which allowed gravity to keep building up pressure. Eventually, gravity won out, and the cloud collapsed into not just one, but two massive black holes. These two black holes had masses of 31,000 and 40,000 times that of the Sun. This showed scientists that the formation of early supermassive black holes might have come from the normal processes of galaxy formation in the young universe. But there's another idea too: primordial black holes. These might have been created just moments after the Big Bang itself. If true, these black holes would have had much more time than other types to grow by pulling in matter. This could explain how some black holes reach supermassive sizes so early. Meanwhile, we already know that many black holes were born from the deaths of the first stars, and scientists have strong evidence to support this. The other theories mentioned above are mostly based on computer models and calculations. To create a supermassive black hole, you need a small area packed with an enormous amount of matter that isn't spinning too fast. Usually, matter in space has a lot of spin, or what scientists call angular momentum, and it takes time for this spin to be pushed outward during the process of accretion, when gas and dust fall into a black hole. This spinning motion is actually one of the biggest things slowing down black hole growth. Accretion is not only the fastest, but also the most noticeable way that black holes gain mass. In fact, most of a supermassive black hole's growth happens during periods when it's swallowing gas very quickly. These dramatic events are what we see as quasars, or active galactic nuclei, which shine brightly from the centers of galaxies. When scientists look far into space, and therefore far back in time, they see that quasars were much more common when the universe was young. This means that many supermassive black holes had already formed and were growing very early in the universe's history. Some incredibly bright quasars have been found that existed when the universe was less than 1 billion years old. This tells us that supermassive black holes had already reached billions of times the mass of the Sun by that time, suggesting they began forming in the first large galaxies. But there's a limit to how big a black hole can grow. According to current theories, the maximum mass for a black hole growing in the usual way, by swallowing gas, is around 50 billion solar masses. Beyond this point, the surrounding gas disk becomes unstable. Instead of feeding the black hole, the gas starts turning into stars that orbit it. The slowdown in growth starts when a black hole reaches about 10 billion solar masses, and past that, it becomes much harder for it to grow. However, in extreme cases, scientists believe it might be possible for a black hole to grow as large as 270 billion solar masses. This would require the black hole to be spinning at nearly its maximum possible speed. Even so, the true upper limit of spin is slightly below the theoretical maximum. Near this maximum mass, something strange happens. The inner part of the disk around the black hole, the innermost stable orbit, becomes larger than the region where the black hole's own gravity dominates. When that happens, the disk can no longer form properly, and the black hole can't grow through accretion anymore. Also, reaching such extreme sizes is very unlikely. To grow that big, a black hole would need to be constantly spinning in the same direction as the material falling into it. But in reality, the material in space often falls in from random directions. This randomness, called chaotic accretion, means that black holes often get pushed in both directions. Sometimes they spin faster, and sometimes they slow down. Over time, these changes tend to slow the black hole's spin more than speed it up. There's more. Black holes also grow by merging with other black holes. But mergers, too, usually end up decreasing the overall spin. All of these effects combined make it very rare for a black hole to grow beyond about 50 billion times the mass of the Sun, especially if it doesn't spin very fast. Only in rare cosmic situations do black holes even approach that massive limit. Even though modern ultra-massive black holes, known as UMBHs, found in quasars and at the centers of galaxies, can't grow larger than about 5 to 27 times 10 billion times the mass of our Sun, at least not through their surrounding disks of falling matter, and especially not given the current age of the universe. Some scientists believe that these cosmic giants might still continue to grow far into the future. In fact, in the very distant future, during the slow collapse of vast groups of galaxies called superclusters, some of these black holes might reach almost unbelievably huge sizes, up to 100 trillion times the mass of the Sun. These enormous black holes play a powerful role in the universe. The strong gravity at the center of many galaxies, where supermassive black holes sit, is thought to be the driving force behind some of the most energetic objects in the cosmos, like Seyfert galaxies and quasars. Interestingly, the size of a black hole at the center of a galaxy often matches the size and mass of the galaxy itself, but this connection changes depending on the kind of galaxy we're looking at. There's even a special link known as the M-sigma relation, which connects the mass of a black hole to how fast the stars in the galaxy's central bulge are moving. Faster star motion usually means a heavier black hole. When scientists talk about an AGN, or active galactic nucleus, they mean a galaxy's center that holds a supermassive black hole actively pulling in matter. This process gives off a lot of light, making the core extremely bright. Our own Milky Way's center, however, isn't quite bright enough to be called an AGN. To explain the many different types of AGNs, astronomers came up with a unified model. This model suggests that the differences we observe mostly come from just a few factors, like how bright the AGN is and what angle we're viewing the black hole's surrounding material from. There are two main types of AGNs. One type mainly shines by giving off light through a thick disk of matter swirling into the black hole, while the other blasts out powerful jets of energy moving close to the speed of light, shooting out from the black hole's poles. When two galaxies, each with their own supermassive black hole, collide and merge, the black holes don't just stay where they are. Because of something called dynamical friction, these black holes slowly drift toward the center of the newly formed galaxy. Eventually, they get close enough, less than 1,000 parsecs apart, to form a pair. As they continue to interact with the surrounding stars and gas, they spiral even closer together, becoming a tightly bound binary system with a gap of just 10 parsecs or less. If they get within just 1,000th of a parsec of each other, the energy released as gravitational waves will finally cause them to merge into one single, massive black hole. After this dramatic collision, the galaxy that formed from the merger will have already settled down, and any initial star-forming fireworks or AGN activity will have faded. But the black hole merger leaves behind something else, a powerful blast of gravitational waves. These waves can give the resulting black hole a giant kick, pushing it through space at thousands of kilometers per second. In some cases, the kick is strong enough to knock the black hole right out of the galaxy. This strange event is known as a gravitational recoil. There's another way a black hole can be thrown out of a galaxy. Imagine two galaxies merging, forming a pair of black holes. Then a third galaxy joins the mix, adding yet another black hole to the center. When three black holes interact, things can get chaotic. Usually, the lightest of the three is flung out into space, while the other two shoot off in the opposite direction as a new binary pair. This kind of three-body gravitational dance is called the slingshot recoil. Any of the three black holes can end up being ejected, and those that get thrown out into space are called runaway black holes. Astronomers have found several clues that might point to such recoiling black holes. For example, if a bright AGN or quasar is not in the middle of a galaxy where we'd expect it to be, that could be a sign. Or, if we find two different light signatures coming from one quasar, it might be a hint that there's a black hole being flung away. Some possible examples of recoiling black holes are in galaxies like NGC 3718, SDSS 1133, 3C 186, E1821 plus 643, and SDSSJ 0927 plus 2943. As for potential runaway black holes, they might include HE 0450-2, 958, CID 42, and objects near the dwarf galaxy RCP 28. Runaway black holes can leave behind a trail of star formation as they move. In fact, a straight line of newly born stars near RCP 28 was once thought to be the wake left by a runaway black hole. But later, research suggested that the feature might just be a small galaxy seen from the side, without a central bulge. And there's a fascinating process called Hawking radiation, named after the famous physicist Stephen Hawking. According to quantum theory, black holes aren't completely black. They slowly give off tiny amounts of heat energy due to strange effects near their edges, called event horizons. This process gradually shrinks the black hole, and if left alone for long enough, it would eventually cause it to disappear completely. For example, if there were a black hole 100 billion times heavier than the Sun, it would take about 2.1 times 10 to the power of 100 years to vanish. And if we imagine an even bigger black hole, one formed during the collapse of a supercluster in the far future, with a mass of 100 trillion suns, it could take about 2.1 times 10 to the power of 1009 years to fully evaporate. Some of the strongest clues that black holes really exist come from a phenomenon known as the Doppler effect. This is the same effect that makes a siren sound different as it moves past you. In space, it affects light. When matter is moving away from us, its light becomes redder, a process called redshifting. When matter is moving toward us, the light becomes bluer, or blue-shifted. Near a black hole, things get really extreme. The matter that orbits close to a black hole has to move incredibly fast, almost as fast as light itself. Because of this, the part of the matter moving away from us appears much fainter, while the part moving toward us looks much brighter. This makes something that is actually evenly shaped, like a ring or disk of matter, look completely uneven and distorted to our eyes. Modern computer-generated images of black holes take this effect into account. One famous example shows what the black hole at the center of our own galaxy, the Milky Way, might look like. This black hole is called Sagittarius A star, and it's based on a scientific model that many experts believe is very accurate. However, our current telescopes still aren't sharp enough to see this level of detail directly, so we rely on simulations for now. Still, scientists have been able to observe something else: matter swirling around farther out from what we believe are black holes. This matter moves much slower than light, which makes it easier to measure. For example, water molecules in space can emit very specific radio signals called masers, which are similar to lasers but with microwaves instead of light. By studying these masers in galaxies near us, scientists have seen very fast, Keplerian motion, meaning the matter is moving in the way predicted by Kepler's laws of planetary motion. This only happens when an enormous amount of mass is packed into a tiny area, something only black holes, or soon-to-be black holes, can explain. For galaxies that are farther away, astronomers can study the width of certain light signals, called broad spectral lines, which gives clues about gas orbiting near the black hole's event horizon, the point of no return. One advanced method, called reverberation mapping, looks at how these light signals change over time to estimate both the black hole's mass and possibly how fast it's spinning. There is strong evidence that our own Milky Way galaxy has a supermassive black hole at its core, about 26,000 light-years from the solar system. This region is known as Sagittarius A star. Scientists have studied a star called S2, which moves in a stretched-out, oval-shaped orbit around this mysterious object. It takes about 15 years and 2 months for S2 to complete one full orbit, and it gets as close as 17 light hours, that's about 120 times the distance between the Earth and the Sun, to the center of the black hole. From how S2 moves, scientists have estimated that the central object must have a mass of about 4 million times the mass of our Sun. Yet, it must fit into a space no larger than 17 light hours across. Otherwise, S2 would crash into it. Another star, S14, has helped show that this mysterious object is even smaller, with a radius of less than 6 1/4 light hours, roughly the size of Uranus's orbit around the Sun. No other known object in the universe, except a black hole, could be this massive and compact. Even more fascinating are the infrared observations of bright flares coming from Sagittarius A star. These show a kind of glowing plasma, hot, charged gas, orbiting incredibly fast, about 30% the speed of light, in tight circles just outside the black hole's point of no return. These flares seem to come from a superheated hotspot on the accretion disk, the spinning disk of matter falling into the black hole. This hotspot appears to follow a circular orbit within a strong magnetic field. On January 5, 2015, NASA observed an X-ray flare from Sagittarius A star that was 400 times brighter than usual, a record-breaking event. Scientists believe this might have been caused either by an asteroid being torn apart as it fell into the black hole, or by magnetic fields twisting and snapping inside the swirling gas. So far, we have rock-solid proof of supermassive black holes in only a few galaxies. These include our Milky Way, the Andromeda Galaxy, also known as M31, a smaller companion galaxy called M32, and a few others outside our local group, like NGC 4395. In these galaxies, the speeds of stars or gas near the center rise dramatically as you move closer inward, which matches what you'd expect if a massive object, a black hole, was pulling them in. In most other galaxies we've observed, these speeds don't rise the same way, so we can't say for sure whether a black hole is there or not. Still, most astronomers believe that nearly every galaxy has a supermassive black hole at its center. This belief comes from something called the M-sigma relation. In simple terms, this means there is a strong link between the mass of a galaxy's central black hole and how fast the stars in the galaxy's bulge are moving around. This pattern has been seen in about 10 galaxies, where we have very accurate measurements, and it suggests that galaxies and their black holes might grow and evolve together. On March 28, 2011, astronomers witnessed something incredible: a supermassive black hole ripping a mid-sized star apart. They saw a sudden burst of X-rays and other signals, and the only explanation that fits is that a star got too close and was torn apart by the black hole's gravity. This happened in a galaxy where the central black hole had been quiet until then. Based on what was seen, scientists think the black hole had a mass of around 1 million times that of the Sun. The event also created powerful jets of material blasting out at high speeds, almost as fast as light, something called a relativistic outflow. A large part of the star likely fell into the black hole, and future observations will help confirm this theory by studying how the light fades over time. The Andromeda Galaxy, which is about 2.5 million light-years from Earth, contains a central black hole about 140 million times the mass of the Sun, much bigger than the one in the Milky Way. An even more massive black hole lives in the giant galaxy Messier 87, located around 48 million light-years away. This black hole is about 6.5 billion solar masses. The largest known black hole in our local region is found in the NGC 4889 galaxy in the Coma Berenices constellation. It is around 336 million light-years from Earth and contains a black hole with a mass estimated at 21 billion times the Sun's mass. When it comes to quasars, extremely bright and distant objects powered by black holes, we use indirect methods to guess their black hole masses. These methods are tricky and come with a lot of uncertainty. One extreme example is the quasar TON 618, which may contain a black hole with a mass of about 40.7 billion times that of the Sun. Its light comes from a time when the universe was still young, with a redshift of 2.219. Other quasars with massive black holes include APM 08279 plus 5255 with about 10 billion solar masses, and SMSSJ 21572 8.21 minus 360215.1 with about 34 billion solar masses, almost 10,000 times bigger than the Milky Way's central black hole. Some galaxies appear to have two supermassive black holes at their centers, forming a pair. If these black holes were to collide, the event would create powerful gravitational waves. This kind of binary system of supermassive black holes is believed to be a common result of galaxies merging. One well-known example is the binary pair in the galaxy OJ 287, which is located 3.5 billion light-years away. This pair contains the most massive black hole ever discovered in such a system, with a mass estimated at 18 billion times the mass of the Sun. In 2011, a supermassive black hole was found in the small galaxy Henais 210, which does not have a bulge. The exact implications of this discovery on the formation of black holes are still unclear, but it might suggest that black holes could have formed before the bulges in galaxies. In 2012, astronomers made another surprising discovery when they found a black hole in the galaxy NGC 1277, which is located 220 million light-years away in the Perseus constellation. This black hole was reported to have an unusually large mass of about 17 billion times the mass of the Sun. This mass is roughly 59% of the mass of the galaxy's bulge, which makes up 14% of the galaxy's total stellar mass. However, other research suggested a different result. The black hole might not be that massive, with an estimated mass ranging from 2 billion to 5 billion times the mass of the Sun, with 5 billion being the most likely value. On February 28, 2013, astronomers used the NuSTAR satellite to measure the spin of a supermassive black hole for the first time. The black hole they studied was in the galaxy NGC 1365, and they found that its event horizon was spinning almost as fast as the speed of light. In September 2014, data from various X-ray telescopes revealed that the very small, dense, and ultra-compact galaxy M60UCD1 contains a black hole at its center with a mass of 20 million times the mass of the Sun. This black hole makes up more than 10% of the total mass of the galaxy. This discovery was surprising because this black hole is 5 times more massive than the one at the center of our Milky Way galaxy, even though M60UCD1 is less than 5,000ths the mass of the Milky Way. Some galaxies do not have supermassive black holes at their centers. While most galaxies without a supermassive black hole are small dwarf galaxies, one case remains puzzling. The supergiant elliptical galaxy, a 2261 BCG, which is one of the largest known galaxies, has not been found to contain an active supermassive black hole with a mass of at least 10 billion times the mass of the Sun, even though it is over 6 times the size and 1,000 times the mass of the Milky Way. However, several studies have suggested that the possible black hole at its center could have a mass anywhere between 6 billion and 10 billion times the mass of the Sun. This suggests that the galaxy might either have a black hole that is not actively growing or one that is smaller than 10 billion times the mass of the Sun. In December 2017, astronomers reported the discovery of the most distant quasar ever found at that time, ULAS J 1342 plus 0928, which contains the farthest supermassive black hole with a redshift of 7.54. This surpassed the previous record held by the quasar Euless J 1120 plus 0641, which had a redshift of 7. In February 2020, astronomers announced the discovery of an eruption in the Ophiuchus supercluster, which was the most energetic event ever detected in the universe since the Big Bang. This event took place in the Ophiuchus cluster, specifically in the galaxy Neve 1, where nearly 270 million times the mass of the Sun's material was being pulled into its central supermassive black hole, which has a mass of 7 billion times the Sun's mass. The eruption lasted around 100 million years and released 5 million times more energy than the most powerful gamma-ray burst ever observed. The eruption produced shock waves and jets of high-energy particles that expanded into the surrounding space, creating a massive cavity about 1.5 million light-years wide, which is 10 times the diameter of the Milky Way. In February 2021, astronomers released a very high-resolution image showing 25,000 active supermassive black holes. This image covered about 4% of the northern celestial hemisphere, and it was created using ultra-low radio wavelengths detected by the Low-Frequency Array, or LOFAR, in Europe. Black holes come in different sizes, and one particularly mysterious type is called the intermediate mass black hole, or IMBH for short. These are black holes whose masses fall somewhere between 100 and 100,000 times the mass of our Sun. That makes them much heavier than the so-called stellar black holes, which form when massive stars die, but not as gigantic as the supermassive black holes, which can weigh more than 1 billion suns. Over the years, astronomers have found a few possible IMBHs in our own Milky Way galaxy, as well as in nearby galaxies. These candidates were not spotted directly, but scientists picked up clues by studying how nearby gas clouds moved, or by looking at the light coming from the material spinning around the black holes, what's known as the accretion disk. One of the most exciting discoveries came from a ripple in the fabric of space-time. On the 21st of May, 2019, at exactly 3 minutes and 2 seconds past 3 in the morning, UTC, scientists detected a gravitational wave event named GW 1905-21. This was the result of 2 black holes smashing into each other, one with 85 solar masses and the other with 65. The collision created a new black hole with a mass of 142 suns. About 8 solar masses were converted into gravitational waves during this massive cosmic crash. This event was officially published on the 2nd of September 2020. Before this dramatic discovery, the strongest hints of intermediate mass black holes came from faintly glowing galaxies called low-luminosity active galactic nuclei. These galaxies are believed to contain black holes because of the way they behave. In some cases, scientists could even estimate the black hole's mass using a method called reverberation mapping. For example, in the spiral galaxy known as NGC 4395, located around 4 million parsecs away, there seems to be a black hole that weighs about 360,000 solar masses. A large group of potential IMBHs, 305 in total, was identified after a detailed analysis of about 1 million galaxy light spectra collected by the Sloan Digital Sky Survey. X-rays were detected from 10 of these candidates, helping to confirm that they really might be intermediate mass black holes. Another type of object that might hide IMBHs is called an ultraluminous X-ray source, or ULX. These extremely bright X-ray spots are often found in galaxies that are bursting with new stars, such as the well-known starburst galaxy M82. ULXs are usually found near young clusters of stars, and scientists think they might be black holes that are feeding on nearby stars. But to prove an IMBH is hiding there, we would need to carefully study the light from the companion star and see how it moves. Some astronomers also suspect that IMBHs might be hiding in globular clusters, those dense, spherical groups of stars that orbit galaxies. By measuring how stars near the center of the cluster move, researchers try to figure out if something massive is lurking there. However, none of the claimed discoveries have held up under closer investigation. One example is a cluster called M31G1. The data could be explained just as easily without needing a big black hole at the center. Gravitational waves may help solve the mystery. If an IMBH pairs up with another black hole or a dense stellar remnant, the spiraling dance of the two objects would send out ripples that telescopes like LIGO and Virgo might catch. There is also a mathematical relationship called the M-sigma relation that predicts how big a black hole should be based on how stars move in the galaxy around it. According to this rule, small galaxies with dimmer centers should have black holes weighing between 10,000 and 1 million solar masses. The smallest black hole predicted by this relation so far lives at the heart of a galaxy known as RGG 118, and it weighs just about 50,000 solar masses. In November of 2004, a team of astronomers announced that they had found the first intermediate mass black hole in the Milky Way. This black hole, named GCIRS 13e, weighs about 1,300 solar masses and sits just 3 light-years from the Milky Way's central giant, Sagittarius A. It's part of a cluster of 7 stars, which might be the leftover remains of a once much larger group of stars that was pulled apart by the powerful gravity of the galactic center. This discovery supports the idea that supermassive black holes grow by swallowing smaller black holes and stars around them. However, the very next year, in 2005, a German research team questioned this finding. After studying how the stars in that cluster moved, they suggested that the black hole might not be there after all. If an intermediate mass black hole really were orbiting near the Milky Way's center, it might be possible to detect it by watching how it disturbs the motion of nearby stars. In January of 2006, another research team, led by Philip Carrett from the University of Iowa, announced an intriguing find. They had observed a repeating signal called a quasi-periodic oscillation from a black hole candidate in galaxy M82. This object, named M82X1, is being fed by a red giant star, which is losing its outer layers to the hungry black hole. The discovery was made using NASA's Rossi X-ray Timing Explorer. However, the rest of the scientific community wasn't fully convinced. The signal they saw only went through about 4 cycles, which might not be enough to confirm that it's truly periodic. It might just be random noise. And even if it is real, scientists aren't sure if it's the orbit of the star or a larger, slower rhythm coming from the black hole's accretion disk. Back in the year 2009, a team of astronomers led by Sean Farrell made an exciting discovery. They found a mysterious object known as HLX-1, which turned out to be a type of black hole that sits between the small, star-sized ones and the gigantic ones found in the centers of galaxies. This type is called an intermediate mass black hole. What made HLX-1 even more interesting was that it seemed to be surrounded by a small group of stars, almost like a tiny galaxy of its own. It was located in a galaxy named ESO 24349. The team believed that this galaxy had once collided with another, smaller galaxy, the one that had HLX-1 in it, and ended up absorbing most of its matter, including the black hole itself. A few years later, on the 9th of July in the year 2012, a group of scientists using the CSIRO radio telescope in Australia announced another major milestone. They had found strong evidence of what they believed to be the first clear example of an intermediate mass black hole. Then, in the year 2015, a research group from Keio University in Japan spotted something unusual. They observed a cloud of gas named CO0.400.22, which had gas particles moving at wildly different speeds. After running computer simulations, they concluded that the best explanation for this behavior was the presence of a black hole with a mass about 100,000 times greater than that of our Sun. However, later studies suggested there might be other explanations, like the powerful shock waves from supernova explosions, which could also make gas clouds behave this way. So, while the discovery was promising, it wasn't definitive. In the year 2017, scientists believed they had found a black hole of a few thousand solar masses hiding in a globular star cluster called 47 Tucanae. They based this idea on how fast and in what direction certain pulsars, special spinning stars, were moving inside the cluster. But later, when more detailed data became available, researchers couldn't find any solid proof to support the existence of a black hole there. Fast forward to the year 2018, once again, the Keio University team made headlines. This time, they discovered several streams of cold gas moving in circles around an unseen object near the center of our galaxy. This object, known by its rather technical name HCN 0.0090.044, seemed to have a mass of about 32,000 suns. If confirmed, it would be the third intermediate mass black hole found in that region of space. In the following year, 2019, scientists detected ripples in space-time known as gravitational waves. These waves came from a powerful cosmic event where two smaller black holes, one 66 times the mass of the Sun and the other 85 times the Sun's mass, collided and merged. The result was a larger black hole with a mass of about 142 suns. The remaining 9 solar masses were released as energy in the form of gravitational waves. This event, known as GW 190521, was an exciting clue in the hunt for black holes that fall into the intermediate category. In the year 2020, astronomers made another possible breakthrough. They spotted a black hole candidate named 3XMMJ 21502 2.40555108, located in the direction of the Aquarius constellation. This possible black hole lies about 740 million light-years away from Earth and could be yet another intermediate mass black hole. A year later, in 2021, astronomers reported finding a black hole weighing about 100,000 times the mass of the Sun. It was located inside a globular cluster called B023G78 in the Andromeda Galaxy. Although the discovery was first published as a scientific preprint, it drew a lot of attention. In the year 2023, astronomers studied the motions of stars in the globular cluster Messier 4, the closest such cluster to Earth. They found an unusually heavy object at the cluster's center, about 800 times the mass of the Sun. Since this heavy object seemed very compact and didn't spread out like a normal group of stars would, scientists suggested it could be a black hole. However, they couldn't completely rule out other explanations, like a tightly packed group of white dwarfs, neutron stars, or regular black holes. Then, on the 10th of July in the year 2024, another intriguing study came out. It looked at 7 fast-moving stars in Omega Centauri, another globular cluster. The stars' behavior suggested they might be orbiting around a hidden black hole with a mass of at least 8,200 suns, another strong candidate for an intermediate mass black hole. Now, here's the bigger mystery. These intermediate mass black holes are too massive to form the way smaller black holes do, which is usually by the collapse of a single star. At the same time, they don't live in the extreme environments where supermassive black holes are thought to form, places like the centers of large galaxies, full of fast-moving stars and intense gravitational forces. So how do these mysterious middle-sized black holes come to exist? Scientists have a few theories. One idea is that many smaller black holes slowly merge together over time. Another possibility is that huge stars in tightly packed star clusters might crash into each other, and the final merged star could collapse into an intermediate black hole. A third, more exotic theory suggests that these black holes were born shortly after the Big Bang itself, making them primordial black holes. There's also an ongoing debate about whether a single, extremely massive star could directly collapse into an intermediate mass black hole. For that to happen, the star would need to be incredibly heavy, more than 260 times the mass of our Sun, before it explodes in a supernova. Some scientists believe this might be possible if multiple stars collide in a young, crowded star cluster and merge into one gigantic star. But even if this can happen, it would be very difficult to spot such a rare and dramatic event. A binary black hole, also called a black hole binary, is a pair of black holes that are locked in a close dance around each other in space. These mysterious cosmic duos fall into two main categories. The first is binary stellar mass black holes, which are formed from the collapse of two very massive stars that were once orbiting each other, or from two black holes that somehow found each other and got pulled into orbit together. The second type is binary supermassive black holes, which are believed to be created when two galaxies crash into each other and their central black holes slowly drift together over time. For many decades, scientists had a tough time proving that binary black holes really existed. The main reason was the nature of black holes themselves. They don't give off light, so they're nearly invisible. On top of that, the tools available to scientists were not sensitive enough to detect them directly. But there was a clue. When two black holes collide and merge into one, they release an enormous burst of energy, not in light, but in something called gravitational waves. These are tiny ripples that travel through space-time, the fabric of the universe itself. Einstein's theory of general relativity, created more than 100 years ago, predicted these waves and even described the unique shapes or waveforms these ripples should have. By the late 20th century and early 21st century, binary black holes had become a hot topic in science. People hoped they could help prove that gravitational waves really existed. That's because the collision of two orbiting black holes would be one of the most powerful sources of gravitational waves anywhere in the universe, and therefore one of the best chances scientists had to detect them. As two black holes orbit each other, they give off these waves, which slowly steal away their energy. Because of this, their orbit shrinks over time, and they spin faster and faster as they spiral toward each other. This slow inward spiral is called the inspiral phase. Eventually, they get so close that they merge into a single black hole. After that, the new black hole goes through a phase known as the ringdown, where it settles into a stable shape, releasing more gravitational waves as it smooths out any wobbling or distortion. During the final split second before merging, the two black holes can reach incredibly high speeds. In that brief moment, the power of the gravitational waves they emit reaches its peak. The first solid proof that binary black holes and gravitational waves are real came in September of the year 2015, when the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, detected a signal named GUON 150,914. This signal was officially announced to the world in February of the year 2016. What LIGO had picked up was the ripple from two black holes, each weighing about 30 times the mass of our Sun, merging together more than 1.3 billion light-years away. In the last 20,000ths of a second before the two black holes collided, they released an incredible amount of energy. In fact, about 3 solar masses worth of material was transformed into pure gravitational energy. At its peak, this burst of energy was being released at a rate of 3.6 times 10 to the power of 49 watts, far more power than all the stars in the entire visible universe combined. Since that discovery, scientists have found more examples of stellar mass black holes merging. But when it comes to supermassive binary black holes, things are trickier. Astronomers have found many promising candidates, but none that have been confirmed without a doubt. These enormous pairs are thought to form when galaxies crash together. Some galaxies, like NGC 6240, show two bright cores, which might be a sign of two supermassive black holes still far apart but slowly coming together. Others, like SDSSJ 104807.74 plus 00554 and EGSD 2J 142033.6 6525917.5, show unusual light patterns suggesting there might be two black holes orbiting very close together. In some galaxies, the central region gives off light in a repeating pattern, almost like a heartbeat. This suggests something large, like a black hole, might be orbiting another one. One well-known example is a galaxy called OJ 287. There's also a galaxy named J0437 plus 2456, where one supermassive black hole seems to be moving unusually fast. This strange motion might be because it's in a pair with another black hole, or possibly even being pushed away after a recent collision, something called a recoiling black hole. Another curious object is a quasar called PKS 1302-102, which seems to have two black holes orbiting each other with a cycle of about 1,900 days. When two galaxies crash into each other, the supermassive black holes at their centers don't usually collide head-on. Instead, they swing past each other like two dancers missing a step, unless something slows them down and pulls them together. The key mechanism that helps them unite is called dynamical friction. As a black hole moves through a cloud of stars, it tugs on them with its gravity. This pulls energy away from the black hole and slows it down. Bit by bit, both black holes lose speed and begin orbiting each other more closely. Eventually, the pair gets so close that they are only a few parsecs apart. A parsec is a little more than 3 light-years. But here's the problem. By this point, they've pushed away most of the nearby stars and gas, which means there's not much left to slow them down further. Without another way to lose energy, their orbits could stall for a very, very long time, longer than the age of the universe. Fortunately, when the two black holes get even closer, just a few thousandths of a parsec apart, gravitational waves take over and start draining their energy quickly. At that point, the black holes are on a direct path to collide, sending out a final, mighty ripple across the universe. Even though it's still a mystery how it happens, scientists believe that supermassive black holes, those gigantic cosmic monsters sitting at the hearts of galaxies, can and do merge together. In fact, astronomers have spotted what looks like a pair of these colossal black holes getting ready to merge in a galaxy known as PKS 1302-102. This discovery is especially interesting because it falls right into a puzzling area scientists call the final parsec problem. The final parsec problem is about figuring out how two black holes that are already close to each other, around 1 parsec apart, a little over 3 light-years, manage to get even closer so they can finally collide. At that distance, the usual ways of losing energy, like giving off gravitational waves, just aren't enough. So, scientists have come up with several possible solutions. One common idea is to bring in extra matter, either stars or gas, close to the pair of black holes. These passing stars or clouds of gas can steal energy from the system, helping the black holes spiral closer together. If enough stars swing by, their gravitational pull can sling some energy away from the orbiting black holes, speeding up the process. Some researchers are even looking into dark matter as part of the solution. But it would have to be a special kind of dark matter, one that interacts with itself. Otherwise, it would just get flung away too soon to be useful. Another possible solution, though it happens rarely, is when a third supermassive black hole comes crashing in because of a second galaxy colliding with the first one. In this chaotic situation, even though one of the 3 black holes might be kicked out, it's more likely that they all stay for a while, bouncing off one another and creating all kinds of unpredictable, messy orbits. This chaos helps in 2 important ways. First, the black holes move through a much larger area of the galaxy, giving them more chances to bump into other stars or clouds of gas and lose energy. Second, their orbits become more stretched out or eccentric, which makes them emit stronger gravitational waves when they swing close together. The life of a black hole pair starts with a stage called the inspiral. This is when the two black holes slowly orbit each other, gradually moving closer over millions or even billions of years. At first, the gravitational waves they emit are extremely weak because the black holes are still far apart. But little by little, they lose energy and their orbit shrinks. Other nearby matter, like passing stars, can also help them lose extra energy by pulling on them. As they get closer, their speed increases, and the gravitational waves get stronger and more powerful. Eventually, they reach a point called the innermost stable circular orbit, often called ISCO. This is the last safe, full orbit before they stop circling and dive straight toward each other. From there, they enter a fast and dramatic final plunge, the actual merger, when the two black holes crash into one another and become one. This is the moment when the gravitational wave signal reaches its highest strength. Right after the merger, the new single black hole is still ringing, like a bell that was just struck. This stage is called the ringdown. During this time, the black hole settles into its final shape, and the ringing dies out as gravitational waves continue to spread outward. This happens especially when the black holes are within a region called the photon sphere, a zone around the black hole where light itself can orbit. Most of the waves disappear into the black hole itself, and only a small fading signal escapes into space, growing quieter and quieter, like echoes fading into silence. A major moment in astronomy happened on the 14th of September 2015, when scientists using the LIGO detector, short for Laser Interferometer Gravitational Wave Observatory, directly observed two black holes merging. These two black holes were around 36 and 29 times the mass of our Sun. When they collided, they formed a new black hole that was about 62 times the mass of the Sun. That means about 3 whole suns worth of mass was turned into pure energy, specifically gravitational waves, in just a tiny fraction of a second. At its peak, this energy release was around 3.6 times 10 to the power of 56 ergs per second. That's more than 200 solar masses being turned into energy every second. To put it in perspective, that's about 50 times more power than all the stars in the entire observable universe combined. The merger itself happened somewhere between 600 million and 1.8 billion years ago, and around 440 megaparsecs away from Earth. That's roughly 1.4 billion light-years distant. The signal detected by LIGO matched up beautifully with what Einstein's theory of general relativity predicted, which was a huge confirmation that scientists are on the right track. To study these kinds of black hole dances, scientists use different kinds of math. During the early inspiral stage, when the black holes are still far apart, a type of simplified math called post-Newtonian approximations is used. These take the basic rules of Newton's gravity and carefully add corrections from Einstein's relativity. Depending on how many corrections are added, they call it second order, 2.5 order, or third order, and so on. There's also another clever method called the effective one-body, EOB, approach. This technique transforms the problem of two orbiting black holes into a simpler one. It treats them like a single object moving in a special kind of space. It's especially helpful when the black holes have very different masses, like when a small black hole is spiraling into a much larger one. After the merger, during the ringdown phase, scientists use black hole perturbation theory. This is a way of calculating how the newly formed black hole wobbles and vibrates before settling down. The final black hole is usually a special type called a Kerr black hole, which spins, and its ringing creates a series of frequencies that scientists can calculate and compare to observations. To fully understand how two black holes come together and merge, scientists need to solve the complete equations of general relativity, a very advanced set of mathematical rules created by Albert Einstein. This is not something we can easily do by hand, so experts use powerful computers in what's called numerical relativity. This method lets scientists create digital models of space and time and watch how they change as two black holes move, spiral toward each other, and eventually merge. In these computer models, it's very important to get two things just right. First, the simulation must be extremely detailed near the black holes themselves, since that's where the strongest gravitational effects happen. Second, the model must be large enough to also capture the gravitational waves, the ripples in space-time, that move far out into the universe. To make this massive task more manageable and faster to compute, scientists sometimes use special ways to describe space, such as Boyer-Lindquist coordinates or fisheye coordinates, which help focus the computer's power where it's needed most. The field of numerical relativity has come a long way since the first attempts back in the 1960s and 1970s. At that time, technology and mathematical tools weren't advanced enough to simulate the entire journey of black holes as they spiral together and merge. But everything changed in the year 2005 when 3 different research teams, working separately, found groundbreaking new methods to finally model the full process: the inspiral, the merger, and the ringdown. These steps describe how the black holes first orbit each other, then collide, and finally settle down into a new, single black hole. In a full simulation, scientists often combine several different methods, each handling a specific part of the black hole dance. These different pieces then have to be carefully connected to form one complete picture. One famous project, called the Lazarus Project, figured out how to stitch the pieces together right at the moment of the merger using a kind of imaginary slice of space called a space-like hypersurface. These computer simulations can tell scientists many interesting things. For example, they can show the binding energy, the amount of energy needed to keep the black holes in orbit around each other. At a stable distance, this energy is at its lowest point. But when they get too close, this minimum turns into something called an inflection point, where the orbit becomes unstable and the black holes fall together. The shape and strength of the gravitational waves, which are crucial for scientists trying to detect them, are also calculated in these models. When the black holes are still spiraling but already deep inside each other's gravitational field, their waves get twisted and bounced around. This creates what is known as the post-Newtonian tail, a kind of echo of the waves that stretches into the past and the future. In the final phase, called the ringdown, the new black hole formed from the merger starts to settle into its final shape. If the final black hole is spinning, as in a Kerr black hole, the twisting of space caused by this spin, known as frame dragging, creates special gravitational waves that match the frequency of the black hole's outer surface or event horizon. But if the new black hole isn't spinning, a Schwarzchild black hole, the final waves are more like fading echoes from the earlier spiral. To understand how the black holes lose energy as they merge, scientists calculate something called the radiation reaction force. This can be done using a clever method called Padé resumation, which helps simplify the math around the outgoing gravitational wave energy. One especially useful tool for this is the Cauchy characteristic extraction technique, or CCE. It helps estimate how much energy escapes out into space without needing to simulate enormous distances. After the merger, the new black hole has a final mass and spin. But even defining the mass isn't simple in general relativity. It depends on the method used. We also know that some of the black hole's original spin, especially around the vertical or z-axis, is carried away by gravitational waves. Scientists figure this out by combining different parts of the waveform with a function called the News function and calculating their effects over time. Another fascinating mystery is the shape of the event horizon, the invisible boundary around a black hole while the merger is happening. To study this, researchers send imaginary test particles through the simulation to see whether they fall into the black hole or escape. As the two black holes get close, the edges of their event horizons stretch out toward each other like the bills of two ducks. These duckbill shapes grow thinner and longer until they touch, forming a narrow X-shaped connection. This connection eventually widens into a kind of tube or bridge between the two black holes. As of the year 2011, no simulations had produced an event horizon shaped like a ring, also known as toroidal topology. However, some scientists believe it could be possible if several black holes orbit one another and merge together all at once. Another surprising outcome of these mergers is that the newly formed black hole can actually get a powerful kick from the gravitational waves. Since the waves carry away momentum, the black hole must move in the opposite direction to balance things out, even though this seems to go against Isaac Newton's third law of motion. In fact, the black hole can be pushed at speeds greater than 1,000 kilometers per second. The most extreme kicks, almost 5,000 kilometers per second, happen when the two black holes are identical in mass and spin, and their spins are aligned just right, either directly opposite or lined up with the plane of their orbit. That's fast enough to shoot a black hole out of an entire galaxy. Most black hole pairs have less perfect alignment, so the kick is usually smaller, maybe just a few hundred kilometers per second. Even so, this can be enough to push black holes out of dense star clusters, stopping them from merging again and reducing the number of gravitational waves we might detect in the future. For black holes that don't spin, the largest kick recorded is about 175 kilometers per second, and it happens when one black hole is 5 times more massive than the other. But with perfectly aligned spinning black holes, a 5,000 kilometer per second recoil is possible. Some key things researchers look at are, when exactly the black holes merge, what mass ratio gives the strongest kick, and how much energy is sent out as gravitational waves. In a direct head-on crash, about 0.2% of the total energy is radiated away as gravitational waves. One of the most promising examples of a supermassive black hole that may have been kicked out, like this, is a mysterious object called CXOJ101527.2 plus 6 25911. In the year 1974, a brilliant physicist named Stephen Hawking proposed a surprising idea that changed the way we understand black holes. He suggested that black holes, which were once thought to trap everything, including light, might actually give off a faint kind of glow. This strange glow is called Hawking radiation, and it comes from just outside the black hole's event horizon, the invisible boundary beyond which nothing can return. This idea was a huge breakthrough. Earlier theories claimed that once light or any other form of radiation passed the event horizon, it could never escape. But Hawking's model, based on the mysterious behavior of tiny particles described by quantum physics, showed that something very different might be happening at the edge of a black hole. Hawking radiation is incredibly weak, so faint that even the most powerful telescopes we have today can't detect it. Yet, this tiny trickle of energy could have huge consequences over time. According to the theory, the radiation slowly takes away a black hole's mass and spinning energy. This means that if a black hole isn't absorbing more matter from its surroundings, it will gradually lose weight and eventually disappear completely. However, for most black holes, this process would take an unimaginably long time, far longer than the current age of the universe. Interestingly, the smaller the black hole, the faster it loses mass through Hawking radiation. This is because the temperature of this radiation, known as the Hawking temperature, is higher for lighter black holes. So, if tiny black holes do exist, like the ones thought to have formed shortly after the Big Bang, called primordial black holes, they would emit much more radiation and shrink much more quickly. In the final moments of their lives, they could vanish in a spectacular flash of high-energy radiation. So far, scientists have not seen such a flash, but they are still searching. The idea of black holes has fascinated scientists for over a century. Modern black holes were first predicted in the year 1915, when Albert Einstein introduced his famous theory of general relativity. It wasn't until about 50 years later that astronomers began to find real evidence that black holes existed in space. What makes black holes so interesting is their small size compared to their enormous gravity. They are incredibly dense and powerful. Some of the earliest studies of black holes were done by scientists like Carl Schwarzchild and John Wheeler. Back then, black holes were thought to be very simple objects with no internal structure, completely empty and with no entropy, which is a measure of disorder or information. A black hole forms when a huge amount of matter or energy is squeezed into a very small space. When this happens, the gravity becomes so strong that nothing, not even light, can escape. The point of no return around a black hole is called the event horizon. Anything that crosses this boundary is lost to the outside universe forever. There's another way to picture this. According to general relativity, space itself can move and stretch. Near a black hole, space can actually fall inward faster than the speed of light. While nothing can move through space faster than light, space itself isn't bound by that rule. So beyond the event horizon, space is rushing inward so quickly that escape is impossible. Once something crosses into a black hole, it falls toward a central point called a singularity. This is a place where gravity becomes infinite and space and time curve infinitely. At that point, all matter is crushed into nothing, leaving behind a warped region of space with no physical substance. A simple black hole with no spin or charge is described only by its mass and the size of its event horizon. But the story doesn't end there. In 1971, two Soviet scientists, Yakov Zeldovich and Alexei Starobinsky, suggested that spinning black holes might be able to create and release particles, similar to how spinning metal spheres can generate electromagnetic energy. The next year, in 1972, a young physicist named Jacob Bekenstein introduced the bold idea that black holes should have entropy, and that this entropy was linked to the surface area of the black hole. Stephen Hawking at first disagreed with Bekenstein. He believed black holes were too simple to have entropy. But after visiting Moscow in 1973 and speaking with Zeldovich, Hawking began to rethink his views. He combined Bekenstein's idea with his own knowledge of quantum physics and Einstein's theory of gravity. In a groundbreaking paper published in 1974, Hawking showed that black holes could give off radiation just like a hot, glowing object, a concept known as blackbody radiation. This energy comes from the black hole itself, which slowly loses energy as particles escape from its edge. Because of Bekenstein's vital contribution, this radiation is now often called Bekenstein-Hawking radiation. Though we haven't yet observed this radiation directly, the theory is one of the most fascinating ideas in modern physics. It links the strange world of quantum mechanics with the powerful pull of gravity, and it hints that even the darkest and most mysterious objects in the universe might not be completely silent after all. Hawking radiation is a strange and fascinating phenomenon that happens near black holes. It all begins with something called vacuum fluctuations. In the empty space around a black hole, tiny bursts of energy can suddenly appear and disappear. These are known as quantum fluctuations. Sometimes, these fluctuations create two tiny particles of light called photons, one just outside the edge of the black hole, called the event horizon, and the other just inside. The one inside gets pulled into the black hole, while the one outside can escape. This escaping particle is what we call Hawking radiation. But this isn't just random. It's deeply connected to two important ideas in physics: the Unruh effect and the equivalence principle. According to the equivalence principle, being near a black hole's edge feels just like accelerating really fast in regular space. Now, here's where it gets even more interesting. If you are very close to the black hole's edge, you would need to accelerate constantly to avoid falling in. From your point of view, it would seem like a warm bath of particles is surrounding you, as if space itself is glowing with heat. These particles appear out of nowhere, turn around, and then fall back in. Now, if this thermal bath of particles exists locally near the black hole's edge, then this warmth must stretch out into the universe in a smooth way. This idea leads to a surprising conclusion. Some of the particles don't fall back in. They keep going and escape into space, becoming part of the Hawking radiation that we can, in theory, detect far away. The black hole itself acts like a kind of stage or background for all these quantum events. In physics, we use something called a quantum field theory to understand how particles behave, and this theory depends on setting certain conditions near the black hole's edge. Once those conditions are known, we can predict what happens to the particles outside the black hole. Even though the event horizon, the edge of the black hole, sounds like a barrier, it's not really a wall. Things can fall in, but they can't come out. And because of gravity's strong pull, someone standing near the edge would feel like they're being pushed by an invisible force, similar to how you'd feel if you were speeding up in space. This person would also feel heat, because space around them is buzzing with energy. As we move farther away from the black hole, gravity becomes weaker, and the heat felt by this observer would seem cooler. This is due to something called gravitational redshift, which is a way of saying that energy, including heat, gets stretched and weakened as it climbs out of the black hole's gravity. Now here's a mind-blowing fact. Forming a black hole is the most efficient way to pack matter into a tiny space, and because of this, black holes have the highest possible entropy, which is a fancy way of measuring how much information or disorder something contains. This leads scientists to believe that all the information inside a black hole might somehow be stored on its surface, not its volume, like a hologram. But here's the twist. As particles escape from the black hole through Hawking radiation, the black hole slowly loses energy. And since energy and mass are connected by Einstein's famous formula E = mc2, losing energy means the black hole also loses mass. This shrinking process is called black hole evaporation. Over a long period of time, the black hole can disappear entirely. The lifespan of a black hole depends on how massive it is. According to calculations, the time it takes for a black hole to evaporate is roughly proportional to the cube of its starting mass. For example, physicist Stephen Hawking estimated that any black hole created during the early days of the universe with a mass of less than about 1 trillion kilograms, that's 1 followed by 12 zeros, would already be gone by now. In the year 1976, physicist Don Page made these predictions more precise. He worked out how much energy a black hole gives off and how long it would take for a black hole's event horizon, or entropy, to be cut in half. This time period is now called the Page time. The situation is more complicated than it seems, because a black hole is not a perfect black object. It doesn't absorb all radiation the same way. The ability of a black hole to absorb or emit energy depends on the spin and frequency of the particles involved. For some types of particles, especially when their wavelength is similar to the size of the black hole, this effect becomes even trickier. Don Page originally thought that black holes could survive until now only if their starting mass was about 400 billion kilograms or more. But back then, he assumed neutrinos, tiny ghost-like particles, had no mass, and that only 2 types of neutrinos existed. Today we know there are 3 types and they all have mass, so the modern estimates are a bit different. For example, a study done in the year 2008, which used modern knowledge of particles and the age of the universe measured by the WMAP space telescope, gave a more accurate estimate of how small a black hole could be and still exist today. Earlier calculations made before the year 1998 used older ideas and gave different results. They suggested that a black hole with the mass of our Sun would take about 10 to the power of 64 years to fully evaporate. That's a number with 64 zeros, a time span much longer than the current age of the universe. A supermassive black hole with a mass of about 100 billion times that of the Sun would take roughly 2 times 10 to the power of 100 years to disappear. And the biggest black holes, Those forming during the collapse of entire galaxy clusters could grow to as much as 100 trillion times the mass of our Sun. These enormous monsters would take as long as 2 times 10 to the power of 1006 years to completely evaporate. However, after the year 1998, updated science changed those numbers a little. For instance, today's estimate for the lifetime of a solar mass black hole is closer to 10 to the power of 67 years. When we talk about the power given off by a black hole as Hawking radiation, we can try to estimate it using the simplest kind of black hole, one that is not spinning and has no electric charge. This type of black hole is called a Schwarzchild black hole, and it only depends on its mass, which we can call m. To figure out how much energy it gives off, scientists combine a few important formulas. One for the size of the black hole, its Schwarzchild radius, another for the radiation given off by hot objects, called the Stefan Boltzmann law, the equation for the black hole's temperature, and the formula for the surface area of a sphere, since the black hole's outer edge, or event horizon, is a kind of spherical shell. When these formulas are put together, a full picture of the black hole's radiation can be built. One important result from these calculations is something called the Bekenstein-Hawking luminosity. This is a fancy way of saying how bright the black hole would be if it only gave off photons, particles of light, and nothing else. It also assumes that all the radiation is coming from the event horizon. But there's a catch. The universe around us is already filled with a very faint glow called the cosmic microwave background radiation, which has a temperature of about 2.7 Kelvin, that's just a bit above absolute zero. For a black hole to actually lose energy and evaporate over time, its temperature must be hotter than this background radiation. According to a study, that would only happen if the black hole's mass was less than 0.8% of Earth's mass. That's roughly the same mass as the Moon. Why does black hole evaporation matter? The idea that black holes can slowly evaporate away changes how we think about them in a big way. First, it helps us understand how black holes fit into the larger story of thermodynamics, the science of heat and energy. It shows that black holes don't just sit there silently. They actually have a kind of thermal behavior, just like stars or hot metal. Unlike most things in the universe, a black hole gets hotter as it loses mass. The more it evaporates, the faster it gets hotter. This temperature rise is exponential, meaning it speeds up very quickly. Eventually, the black hole is expected to end its life in a powerful and explosive flash of gamma rays, some of the most energetic light in the universe. When the black hole shrinks down to the tiniest possible size, close to 1 Planck mass, its size becomes as small as 2 Planck lengths, which are unimaginably tiny. At that point, we would need a whole new theory called quantum gravity to fully understand what's going on. Here's where things get even stranger. The basic models of black hole evaporation lead to what's called the black hole information paradox. When a black hole disappears, it seems like all the information about what went into it is just gone. But that's a big problem in physics, because information is supposed to be preserved in the universe. Some scientists think maybe the Hawking radiation does carry this missing information, just in a very scrambled way. Others believe the black hole might leave behind a tiny remnant particle that holds all the lost data, and some suggest that maybe, under extreme conditions like this, information really can be lost. Another puzzle is called the trans-Planckian problem. Hawking's original idea involved particles that, near the black hole's horizon, seem to have wavelengths smaller than the Planck length, so small that the laws of physics, as we know them, don't apply. This happens because of how time behaves near a black hole. From far away, it looks like time freezes at the horizon. So, when a particle is emitted with a normal frequency, if we trace it back in time to where it came from, it would seem to have had an infinite frequency at the horizon. There's also something called the Unruh effect, which is similar to the Hawking effect. Both involve how light waves, or field modes, change frequency depending on how you're moving. Near a black hole, staying in place actually requires constant acceleration, and this changes the light waves you detect through something called Doppler shifting. If we follow a single photon of Hawking radiation back in time, we find that its frequency increases wildly the closer it gets to the black hole's edge. Its wavelength shrinks more and more to the point that it becomes nearly zero, again smaller than the Planck length. In one version of the black hole model, the maximally extended Schwarzchild solution, the photon's frequency stays well behaved only if we trace it into a region of space that existed before the black hole was born, a region no observer can actually reach. Hawking instead used a more practical model, where the black hole is born at a specific moment in the past. In that case, all the radiation we eventually see comes from a tiny, microscopic point at the very moment the black hole first formed. The little quantum fluctuations at that exact point are what give rise to all the future radiation. But because these waves start out extremely close to the event horizon and spend a long time there, they get stretched out massively, redshifted, and begin their lives as ultra-short wavelengths, far smaller than anything our current physics can describe. Because of that, many physicists still argue over whether Hawking's original calculations are truly correct, since they rely on physics at distances we simply don't understand yet. Today, many scientists believe that the so-called trans-Planckian problem is mostly a mathematical issue that shows up when we try to calculate things around the edges of black holes, also known as horizons. A similar situation happens with white holes, which are like the opposite of black holes. If normal matter falls toward a white hole, it piles up on the surface because there's no future path for it to continue into, no way forward. If we try to follow what happens to this matter in time, we find that it gets squeezed more and more until it ends up in a strange and extreme region where the usual laws of physics break down. This is called the trans-Planckian region. This breakdown happens because the waves, or modes, that reach the horizon from the perspective of someone watching from the outside become infinitely high in frequency. This makes the calculations blow up. The only way to make sense of what's going on is to switch to a different set of coordinates, ones that go smoothly across the horizon, to look at things from a new angle. There are other ways of looking at this problem, especially when thinking about Hawking radiation, which is the theoretical glow black holes give off as they lose energy. Some of these new ideas try to fix the trans-Planckian problem. For example, a similar issue pops up in the Unruh effect, where someone speeding up through empty space would feel like they're being bathed in warm radiation. The temperature in the Unruh effect can be calculated using basic physics, and most scientists agree that it makes sense. This suggests that we might be able to handle the trans-Planckian problem in a similar way. However, the formulas we use for these effects only work if gravity behaves normally down to incredibly tiny scales, specifically the Planck scale. This is the realm of unimaginably small things. For example, a black hole that is lighter than the Planck mass, which is about 10 to the power of -8 kilograms, would be predicted to disappear in a time shorter than the Planck time, about 10 to the power of -43 seconds. Since these results don't make sense in reality, many researchers believe the Planck mass is the smallest possible mass a black hole can have. But things change in theories that include large extra dimensions. These are ideas where our universe has 10 or even 11 dimensions, not just the familiar 3 of space and 1 of time. In these theories, the constants of physics, including the Planck constants, could be very different. This would mean we'd also need to adjust our formulas for Hawking radiation. If a tiny black hole had a radius smaller than these extra dimensions, its lifetime would follow different rules, as shown in scientific papers by Chung in the year 2002 and Carr in the year 2005. To understand what's happening around black holes in more detail, scientists have studied their structure using a theory called loop quantum gravity. This approach doesn't automatically reproduce the famous formula for black hole entropy that was first discovered by Jacob Bekenstein and Stephen Hawking unless a certain adjustable number in the theory is set just right. Even though this is a bit of a workaround, the theory still allows physicists to calculate new effects of quantum gravity on black hole entropy and radiation. Interestingly, when we look at the tiny changes in the surface area of a black hole caused by quantum effects, we find that a quantum black hole would not radiate energy in a smooth, continuous way. Instead, it would give off radiation at specific, sharp frequencies, like a musical instrument playing certain notes on top of the usual Hawking radiation. These signals could possibly be detected if we ever observe X-rays from evaporating primordial black holes, which are ancient black holes formed in the early universe. In June of 2008, NASA launched the Fermi Space Telescope to search for powerful bursts of gamma rays that might come from these tiny black holes as they disappear. But as of January 1st, 2024, no such signals have been found. If the theories about large extra dimensions turn out to be true, then the Large Hadron Collider at CERN might be able to create mini black holes in the lab and watch them vanish. However, no such micro black holes have been seen so far. Under real-world laboratory conditions, the effects of Hawking radiation are far too small to detect directly. But scientists have come up with clever ways to study it by using analog black holes. These are systems where something like a fluid mimics the behavior of gravity. For example, in sonic black holes, sound waves act like light near a real black hole, and the flow of a nearly perfect fluid acts like gravity. In some experiments using Bose-Einstein condensates, a special state of matter at extremely low temperatures, researchers have even reported signs of Hawking-like radiation. In September of 2010, an experiment in a lab created a kind of artificial white hole, a place where light could not enter. The researchers claimed that this setup produced light waves similar to Hawking radiation. However, these results have not yet been confirmed, and many scientists are still debating whether the experiment truly demonstrated the effect. In Albert Einstein's theory of general relativity, there is a special mathematical solution called the Schwarzchild metric, sometimes also called the Schwarzchild solution. This solution helps describe how gravity behaves around a perfectly round object like a planet or a star, as long as we assume that the object has no electric charge, no spin, and that the universe's overall expansion, known as the cosmological constant, is not affecting it. In other words, it's a clean and simple situation where gravity is the only thing at play. This solution turns out to be very useful in real life, especially when studying stars, planets, or even our own Earth and the Sun, objects that are not spinning too quickly. The Schwarzchild solution was discovered by a German physicist named Carl Schwarzchild in the year 1916. A helpful rule in general relativity, known as Birkhoff's theorem, tells us that the Schwarzchild metric is actually the most general way to describe any situation where there's no matter around, a vacuum, and the mass involved is round and still. When such a massive object collapses and becomes so dense that not even light can escape it, it turns into a black hole. If this black hole doesn't spin and doesn't have any electric charge, it is called a Schwarzchild black hole, or a static black hole. These types of black holes are all the same, except for one thing: their mass. What makes a black hole so mysterious and fascinating is a boundary around it called the event horizon. This boundary isn't made of any kind of physical material. It's not a wall or a surface you can touch. Instead, it's a sort of invisible one-way gate. If a person or object were to fall past this boundary, they wouldn't notice anything special at first, but they would be trapped, unable to escape the black hole's pull, and would eventually be destroyed by its intense gravity. The distance from the center of the black hole to this boundary is known as the Schwarzchild radius, which is often simply called the radius of a black hole. Any non-spinning and uncharged object that becomes smaller than its own Schwarzchild radius will turn into a black hole. What's truly interesting is that this solution to Einstein's equations works for any amount of mass. So in theory, a black hole could form from any size of mass. as long as the conditions are just right. Close to a Schwarzchild black hole, the space around it bends so much that even light gets pulled in strange ways. Light that passes very close to the black hole can be bent so much that it loops around the black hole several times before escaping, or not escaping at all. The Schwarzchild solution is named to honor Carl Schwarzchild, who figured out the exact solution in the year 1915, just a little over a month after Albert Einstein published his theory of general relativity. Schwarzchild published his results in January of 1916. Sadly, he passed away not long after, due to a disease called pemphigus, which he developed while serving in the German army during World War I. Interestingly, another physicist named Johannes Droste independently came up with the same solution in the same year, 1916, using a simpler method. In the early days of general relativity, many scientists were confused about some strange points in the Schwarzchild solution, especially about places where the math seemed to break down, called singularities. In his original paper, Schwarzchild placed what we now know as the event horizon at the very center of his coordinate system. He introduced a helpful mathematical tool called the Schwarzchild radial coordinate, which helped describe the space around a black hole. However, his version of this coordinate was different from how we understand it today. Later on, in the early 1920s, two scientists, Paul Painlevé in 1921 and Olvar Gullstrand in 1922, each came up with a new way to describe the Schwarzchild solution using different coordinates. These are now called the Gullstrand-Painlevé coordinates. Their version removed one of the mathematical singularities, but unfortunately, they didn't realize that they were just using a different point of view, a coordinate transformation, and they mistakenly believed that this proved Einstein's theory was wrong. In 1924, the British astronomer Arthur Eddington introduced another coordinate transformation, now known as the Eddington-Finkelstein coordinates, which also removed the false singularity. However, even Eddington didn't fully understand how important his discovery was. Then, in 1932, a Belgian physicist named Georges Lemaitre came up with yet another coordinate transformation, now known as the Lemaitre coordinates. He was the first to clearly understand that the so-called singularity at the Schwarzchild radius wasn't a real physical object. It was just a mathematical illusion caused by using the wrong coordinates. Finally, in 1939, an American physicist named Howard Robertson showed that a person freely falling into a black hole would actually pass through the event horizon in a limited amount of time, according to their own clock, even though it would seem to take forever when viewed from far away. This helped clear up more confusion and gave scientists a better understanding of how black holes really behave. Back in the year 1950, a physicist named John Singh wrote a fascinating paper that made an important discovery about black holes. He showed that what many believe to be a deadly singularity at a certain point, known as r equals r sub s, was not actually a real physical problem. Instead, it was just a trick of the coordinates being used. In simpler terms, it was like looking at a map where two streets seem to crash into each other, but only because the map was drawn badly. When you redraw the map more clearly, you realize there's no crash at all. This point, r equals r sub s, actually represented not one, but two different horizons, or boundaries in space. Later, this same insight was independently rediscovered by two other scientists, George Szekeres and Martin Kruskal. They created a new way of looking at space and time around a black hole using what are now called the Kruskal-Szekeres coordinates. Their method was even simpler than Singh's, and it helped describe the entire region of space and time affected by a black hole with just one consistent system of coordinates. However, many people at the time didn't notice these discoveries. That's likely because the original papers by Georges Lemaitre and John Singh were published in lesser-known journals. Even famous scientists like Albert Einstein still believed that the strange behavior at r equals r sub s was a true physical singularity, a place where the laws of physics completely break down. Later on, Singh came back to the problem and showed how to get the Schwarzchild solution in a more thoughtful way. He didn't want to start with bad coordinates, like the original Schwarzchild ones, and then fix them. He wanted to begin with better ones from the start. Sadly, his careful work didn't get much attention in the scientific community, even though it was appreciated by another famous physicist named Subrahmanyan Chandrasekhar, who used it in his important book about black holes. The real turning point came during the 1960s, when new and more advanced mathematics, especially something called differential geometry, was brought into the study of general relativity. This allowed scientists to describe space and time more precisely and to finally understand what it really meant for a region to have a singularity. Thanks to this, scientists could now clearly define the point r equals r sub s, not as a physical singularity, but as something called an event horizon. This is a kind of invisible boundary in space that you can only pass through in one direction. Once you're in, there's no coming back. Now, in the Schwarzchild solution, which is one of the earliest mathematical models of a black hole, there seem to be two troubling points, one at r equals 0 and another at r equals r sub s. At these points, some numbers in the equations go wild. They either become infinite or involve dividing by 0. But this only matters if these points are inside the actual object we're talking about. For example, the Sun has a radius of about 700,000 kilometers, while its Schwarzchild radius, the size it would have to shrink to in order to become a black hole, is only about 3 kilometers. So there's no danger of a singularity unless a star gets much smaller than it normally is. The so-called singularity at r equals r sub s divides the Schwarzchild coordinates into two completely separate parts. The outer region, where r is greater than r sub s, is the one we see around stars and planets. The inner region, from r equals 0 to r equals r sub s, contains the true singularity at the center, but is completely cut off from the outer world by the event horizon. The Schwarzchild coordinates don't provide a way to connect these two regions directly, so they appear like two separate universes. But here's the twist. The singularity at r equals r sub s is actually not real. It's what scientists call a coordinate singularity, an illusion created by using the wrong map. If you change the map, in other words, use different coordinates like the Lemaitre, Eddington-Finkelstein, Kruskal-Szekeres, Novikov, or Goulstrand-Painlevé systems, you'll see that everything works fine at r equals r sub s. With the right coordinates, you can describe both the inside and the outside of the black hole in a continuous and smooth way. However, r equals 0 is a completely different matter. This is where things truly fall apart. If you insist that the mathematical solution must work all the way down to the very center of the black hole, you encounter a real singularity, a place where the fabric of space and time itself breaks down. Unlike the coordinate singularity, this gravitational singularity cannot be fixed by changing the coordinates. You have to look at deeper properties of space-time that are the same no matter what map you use. The Schwarzchild solution can be written using many different types of coordinates. Each version highlights a different aspect of how gravity works near a black hole. For example, there's a clever way to visualize the space around a black hole using something called Flamm's paraboloid, a curved shape that helps us picture how space bends. But don't confuse this with the classic gravity well you might see in science exhibits. No real object, massive or not, can actually move along the surface of this paraboloid, because that surface exists all at once in time. Any object moving there would have to travel faster than light, which is impossible for anything with mass. Only hypothetical faster-than-light particles, called tachyons, could do that, and even they would still feel the pull of gravity toward the center. Moving objects like planets usually follow non-circular orbits, which behave a bit differently in Einstein's gravity than they would in Newton's. For instance, the planet Mercury spends more time close to the Sun than Newton's laws would predict. This is just a mild version of what happens to anything that crosses the event horizon. It falls in and never comes back. Between these two cases, there are even stranger possibilities, like knife-edge orbits, where a satellite loops around the black hole many times in almost perfect circles before shooting outward again. The Schwarzchild solution also has a special kind of symmetry. It respects rotations and reflections in space, as well as shifts in time, but not in space. This means it belongs to a smaller part of the bigger Poincaré group, the group of all possible motions in spacetime. This subgroup has 4 dimensions and includes the normal version, doing nothing, reversing time, flipping space, or doing both at once. In this Schwarzchild spacetime, 2 important mathematical tools, the Ricci curvature scalar and the Ricci curvature tensor, both come out to be 0. To really understand what this means, scientists often use an orthonormal basis, which is a sort of standardized measuring tool for curved space. Interestingly, these quantities don't change even if the observer is moving. And through something called the geodesic deviation equation, we learn how 2 nearby observers are pushed apart or pulled together by the tidal forces of gravity.